I'd like to thank the organizer for the opportunity to come back here. I was here 25 years ago for a workshop. A lot of the place remains the same. There's been a few improvements. We have internet now. I don't remember having internet back 25 years ago. But yes, many nice features here. So I'm going to talk about a bunch of things here. Some of it's going to be very introductional, so we're going to go quickly through that. If you have a question, ask the question during the talk. Raise your hand and ask the question. It'll make it more fun for me and for you to have that interchange. So I work at the University of Tennessee, located in Knoxville. I also have a position at Oak Ridge National Laboratory, about 40 kilometers away. And then I spend the month of July, usually, at the University of Manchester in England, working with people there on a number of things, about 4,000 kilometers from Knoxville. Okay, so you know the story as well as I do. Simulation's a big deal today. We consider it the third pillar of science, next to theory and experimentation. Computers do things that we can't do with theory, and we can't do through a physical experiment. We can't do them with a physical experiment. So we simulate stuff. And today, simulation drives science. That's the big deal. At Oak Ridge National Laboratory, at all DOE laboratories, computational simulation is the way in which science is done. They invest in large computers to help with that, and they devote significant resources to making computational science work. So we do this because we do simulation because perhaps it's too difficult to build a physical device like a wind tunnel, or it's too expensive to carry out an experiment where we do something to a jet aircraft, like inject birds into the engine, suck them into the engine, and see what happens to the engine and see what happens to the aircraft. So that experiment was done. That's an expensive experiment to do. We can do that on a computer. So we simulate that today to make better designs that can withstand those kind of impacts. Sometimes things happen too slowly, and we want to understand what happens to that physical phenomena, like two galaxies colliding. That's an experiment that's very hard to do, and we have a hard time seeing that in real time. So we simulate that to understand what the behavior is. So computers allow us to do that. And sometimes it's too dangerous to carry out the physical experiment. You know, in the old days, when we were developing nuclear weapons, we would go out and into the desert, drill a hole, stick something down in the ground, and light the fuse and see what happens. Well, they don't do that anymore. So we do simulation to understand what happens when they construct and devise certain devices. So computation is this paradigm for using high-performance computing to simulate physical phenomena. And you know, again, we do it because well, we can. We do it because we want to understand better how to design vehicles which can withstand crashes. So we do an ensemble calculation to get an optimized set of parameters so that collision will protect the driver and do minimum damage to the vehicle. We design drugs that can effectively combat certain diseases. That's done on a computer to help better understand how that drug should be designed. At the Department of Energy, they do a number of things related to energy research. The Department of Energy has two sides. One side does defense work. So think of those guys doing weapons research. That's an energy-related thing. And they also do something called open science, and that's related to unclassified work dealing with energy. So at my laboratory, at Oak Ridge, we do open science work, and that's involved with energy storage, designing biofuels, looking at turbulence, trying to design better combustion engines, looking at smart trucks, aerodynamically designed trucks that can get better fuel economy, looking at nuclear energy, designing reactors that can better do things, and looking at nanoscience to produce better products. Those are some of the things that take place at the open science labs. DOE is a heavy buyer of high-performance computing, There are basically 6 DOE laboratories. 3 of them do defense-related stuff. Those are Los Alamos, Livermore, and Sandia National Labs. And then 3 do open science, unclassified work. That's Argonne, Oak Ridge, and Lawrence Berkeley National Laboratory. So that's how things roughly are cut. And they have a large group of computational scientists working in those areas. I think of computational science as sort of fusing together 3 things. It takes domain scientists in a certain area like biology, physics, chemistry, along with computer scientists and mathematicians to form a team to work on a problem. That's the way computational science is sort of done and progresses at the Department of Energy laboratories today. It's that team that engages in the design and effectively solving problems. The problems that are solved are computationally intensive for the most part, but they can also be data intensive. And we're starting to see more and more data intensive problems come up. And I think in the future, things like deep learning is going to play an important part in our understanding of what goes on, and that'll be a tool that we use to help in analyzing things, and that has a very large data-intensive component. It also has a computational component as well. Okay, so there's a range of applications that we use high-performance computing for. This is just a short list. We can go on with a list. I think you know this as well as I do. We use them for aircraft wing design. We use them for noise reduction. We use them for making computational materials better. We use them for deep learning and all sorts of things. High-performance computing is important for the economy. You take a look at what happens when a hurricane strikes the coast, and you have to prepare for that, so you design a model to understand where that hurricane will strike the coast. It costs about $1 million per mile that you have to evacuate. So you want to minimize the area where you do the evacuation, but you also want to get it right, so you don't miss that area where the hurricane will strike. So high-performance computers help in doing the prediction about where these things are going, and you can save significant amounts of money by limiting the evacuation zone that you do for these kind of events. The weather is the way we see supercomputing touching all of us. I talk to my mother. She has no idea what I really do. She thinks I do something with computers. And I say, well, I work on these high-performance computers, and we design algorithms, and she has no idea what an algorithm is. But I say, well, take a look at the weather tonight. And the stuff that goes on in predicting the weather is using a high-performance machine. So that's something which touches us on a daily basis. And sometimes they get it right. Sometimes it doesn't work out exactly as the prediction is, and I don't know what happened on Friday, but hopefully that's not going to happen this Friday. Okay, so we want to look at high-performance machines. These things are used, again, they have the strategic value. They're critical for national security. They're fundamental contributors to the economy, and they're tools for doing business. You know this story as well as I do. We've seen this incredible change take place in a short period of time, changes in the performance of our computers. In the past decade, we've seen this amazing situation. Microprocessors have become smaller, denser, and more powerful, and the result is that microprocessor-based supercomputing is the thing that we do today. One time we had companies that built supercomputers. That's all they did, build supercomputers. And microprocessors were used for our desks and laptop computers, but that's changed in a very significant way. The market is not there to sustain just building supercomputers, so we don't design special purpose hardware like that any longer. We use microprocessors. They sort of grew up. So Moore's Law, Gordon Moore, one of the founders of Intel back in 1965, made this incredible prediction. He published this paper based on these 5 points that he had. He said that the number of gates on the chips that are designed is going to double every 18 months. So that's an incredible situation that took place. So the number of transistors on chips will double every 18 months. And looking at what Intel has done, we see that exponential rate with Intel processors, the number of transistors, to this incredible level that we have today. But that just gives us transistors. That just gives us transistors. And how does that really help high-performance computing? Well, the real secret sauce with Moore's law is Dennard scaling. So Robert Dennard is a researcher at IBM Watson Research. So Moore's law is giving us more transistors, but Dennard scaling makes them useful. You know, in the old days, I would have a computer, and when I got my new computer, it ran faster. And I was a happy guy because it ran faster. And that's because of Dennard scaling, not because of Moore's law totally. So Dennard observed that the voltage and current should be proportional to the linear dimension of the transistor. So transistors are getting smaller as we do this shrink. So we're going to decrease the size by some factor. And Dennard says, well, we can decrease the voltage by that factor as well. And we're going to increase the number of transistors by that factor squared, because it's an area kind of thing. And the clock speed can be increased by that factor. And the energy consumption doesn't change. That's the magic that goes on here. The energy doesn't change under those conditions. So you get all this effect of shrinking, more transistors, and the energy used to power that thing doesn't change. That's incredible. So you get twice the transistor count, 40% faster, and 50% more efficient. So in the old days, when I got my new computer, I took my application from that old computer, put it on the new one, and it ran faster. I didn't have to do anything. It just ran faster. So that's sort of amazing, right? Amazing change. That's because of Dennard scaling. So unfortunately, Dennard scaling has a limit. And that limit, or Dennard scaling, breaks down as the result of the small feature sizes that we have in the gates that we have today. And that causes a leakage of voltage, and that leakage causes the chip to heat up. So that becomes the problem, is that heat situation. So today, if you notice, the chips that we have are roughly at about 100 watts, roughly 100 watts. And that's because of this effect of Dennard scaling breaking down. That breakdown took place in 2004. So we got Moore's law giving us all these transistors. Dennard scaling was doing well up until 2004, and then it flattened out. I can't increase the cycle time anymore of our processors. The processor cycle time is fixed. The power budget is fixed at 100 watts. I can't have something about the size of your fingernail being much hotter than 100 watts and having it cooled through conventional methods. So all those transistors, what are we going to do with them? We're going to make more processors on the chip. So that's how multi-core gets started. More processors on the chip because of Moore's law, giving us that ability to enhance the number of transistors. So Moore's law is going to continue. It's slowing down. It's not giving us that factor of 2 every 18 months. It is slowing down. And that's going to cause, ultimately, everything comes to an end. Ultimately, that'll come to an end. But it's just slowing down. It's not coming to an end in my lifetime, I'll say. OK, so this is another way to view this. Transistors are going up over time. That causes changes in frequency has gone up because of Dennard scaling until that 2004 point where we have to freeze that. And then multi-core kicks in with the additional cores on the chip, on the substrate, on the socket. And the power has been going up, and that gets frozen as a result of the cycle time being frozen. So here's sort of the, OK, so that hardware issue, the hardware issue about Dennard scaling became a software problem. Because now when I get my new computer, it's going to be faster, but I've got to do something to get that performance boost. It's going to be faster because it has more cores. But I have to do something. I have to write a parallel program. So now that hardware problem just became a software issue.
But
Yeah.
It'll only get faster if the cores are the thing that determine how fast it goes.
That's right. So there's many things in a computer that determine how fast your program goes. That's the first thing we look at is the processor, and we'll talk about some of the other things as we go on. OK, here's another way to cut this. The power consumed by our processors looks something like, it's proportional to the voltage squared times the frequency of the processor. Voltage squared times frequency, that's the power consumed. The frequency for semiconductors today looks like the voltage. It's proportional to the voltage. So that says the power looks something like the frequency cubed. So let's say I had something running at a certain frequency and I double the frequency, make it run twice as fast. What happens to the power? Goes up by a factor of 8, right? So if I think about taking that chip that's running at, let's say, 300 gigahertz or 3 gigahertz, and I want to double it, I've got something that's going to be 800 watts that I have to cool, and that's something that becomes untenable for our design point. So that's controlling things. And the architects know this, and that's what gives us this. So if you enhance the frequency by 0.5, that gives the power requirement 3.3 times. It gives you a performance of 1.5, however, but that's the power that's needed to drive that thing, the amount of energy needed, essentially. And for multi-core, if I give you 2 cores on a chip and reduce the cycle time, I can give you that same kind of performance, but with a less power budget. So multi-core is sort of driving in this direction, right? That's what multi-core is doing for us. Okay. And multi-core, everything is multi-core today, right? Everything is. We've got Intel processors, conventional Intel processors, 18 cores. Intel's special thing that used to be called an accelerator. Xeon Phi is at 72 cores. IBM has things. AMD has processors. Fujitsu does. If you take a look at the GPU from NVIDIA, it has 2,688 CUDA cores, and those translate into what I call 14 regular cores. There's 14 independent streams of instruction there that are being executed by lots of those CUDA cores underneath. The Shenwei processor, we'll talk about this in a moment, it has 260 cores. So this is a chip that was designed in China and is being used today in the most powerful supercomputer. Okay, just as a rough way, this is how we're building supercomputers today. We think about taking a chip, a socket, which has a number of cores on it. In this cartoon, it's got 4 cores. And we think about using that, and you can write a program for that. It's going to have shared memory. The cores can see the memory. They can see all the memory. They share it. It's a global address space, and they can communicate across that memory space, implicitly perhaps, if they're doing shared memory. And we're going to take that chip and we're going to put it on a board. So we're going to take a board now and put multiple chips on it. And we're going to write, and perhaps we're going to augment those chips with a GPU. So we're going to stick a GPU, a graphics processor next to it to accelerate the performance that we see from that. It's a thing that's going to boost the performance of this chip. And the way this works, the way you should think of it, is you're going to offload data to this GPU and start a computation on it. And asynchronously, it's going to do something, and then later you're going to go back and grab the data and bring it back to you. So it's working with this guy. It's working with him to accelerate the performance over some link. And we're going to program it in the same way, perhaps shared memory. Perhaps one board has a whole chunk of memory, and all the processors can see that memory, and they all have equal access to that memory through a shared address space. And we're not going to be satisfied with that. We're going to take that board and stick it into a cabinet. So we're going to fill up a cabinet with those boards. And again, if we're looking at programming this thing, we may be programming it using shared memory within the node. Maybe OpenMP is the programming paradigm that we use there. And if we go across boards, we may be using MPI to do the programming, to pass messages between the processes in various points in this machine. And we're not going to be satisfied with that. We're going to fill up a room with multiple cabinets. So today, for supercomputers, the room is about the size of a basketball court. Think of it that way, full of cabinets, right? And your program is going to be running across that ensemble of hardware devices there. And there's many issues that will impact performance, as we will see when running in this kind of environment. Okay, we're going to talk about performance, and we're going to talk about flops. So flops are floating point operations per second. Whenever I talk about a flop, I'm talking about 64-bit floating point operations. And the operations I'm talking about are adds and multiplies. So adds and multiplies with 64-bit operands. And we're going to talk about theoretical peak performance. So if we take a processor, we're going to look at its theoretical peak performance. And that's based on a paper and pencil calculation. Right? We're going to look at the cycle time, how many operations it can do per cycle, and we're going to compute that theoretical peak performance. So just as an example, this is an old processor, an Intel Xeon processor. It's got 4 cores on that chip, so 4 cores on the chip. The cycle time is 2.93 gigahertz. So 2.93 billion instructions per second could be issued by this guy, right? So that's billion, 10 to the 9 instructions per second. So I still have a hard time grasping that concept. And each core does 4 floating point operations. It can complete 4 floating point operations per cycle, right? That's the rate at which it finishes operations. There's a pipeline. Once that pipeline gets filled, it's completing 4 per cycle. So the theoretical peak for this guy is 4 times 2.93. That gives you 11.72 gigaflops, 11.72 billion floating point operations per second. That's out of 1 core. You got 4 cores here. So that chip is at 46 gigaflops. That's the theoretical peak performance for that chip. That's an incredible rate. That's a commodity processor. That's amazing. Just amazing. It's stunning. I have a hard time with these numbers. So that's where we are in terms of the theoretical peak performance. And of course, we're interested in what we can achieve on that. What do we really get out of that for our computations? Okay, so we're going to take a look at a benchmark. So this benchmark's been around for a few years, 24 years, since the last time I came here, basically. It's put together by a bunch of people. So Hans Moyer was a professor at Mannheim University. He's dead. Horst Simon and Eric Strohmeyer work at Lawrence Berkeley National Laboratory. And I'm the other person on this list. So every 6 months, we come up with this list of the 500 fastest computers. And they're ranked according to a benchmark. And we can argue if this is a good or a bad benchmark. I'm going to argue later about the goodness or badness of it. So let's not have that argument right now. So it's called the LINPACK benchmark. The LINPACK benchmark says we're going to solve this problem, AX equals B, where A is a dense matrix. So I'm going to give you a matrix A and a right-hand side B. And to do this test, you have to solve that problem. And the other constraint is you have to solve it using Gauss elimination with partial pivoting. You must use that algorithm. There's some other minor things. You have to do 64-bit floating point arithmetic. We're going to check to see that you got the right answer. And we're going to ask you to solve it running as fast as possible. So optimize that algorithm, implement it the best you can on your hardware, and solve that problem. I'm going to give you the matrix, and then I'm going to check your answer. So basically what happens is, as the matrix size increases, the performance rate goes up until you reach some asymptotic point. And that's what we'd like to capture for your machine, that asymptotic point. So you're going to solve a big problem. The computers today, the big ones, they fill the whole memory up with a matrix, and they solve it. So the matrices are about size 10 million. On the fastest computer, it takes about 3.5 hours to solve that problem. A 10 million by 10 million dense matrix takes about 3.5 hours. Okay, this list is updated twice a year. It's updated in June and in November, so the most recent results are from June. It's updated at the big supercomputing meeting in the US. This year it'll be held in Salt Lake City. So about 10,000 of my closest friends go to that meeting. So it's a big homecoming. There's about 2,000, maybe 3,000 people go to the meeting in Germany. So it's always a lot of fun. And there's a website that contains all the data. So here's a snapshot of high-performance computing from 1993, when we started, until today. So the way to read this is, this red line here is charting number 1. That's the fastest computer. It's at 93 petaflops, 93 times 10 to the 15 floating point operations per second. Right? That's the rate at which it solved the problem. This is the guy at the bottom of the list. So that's number 500. It just made the list, 286 teraflops. And this orange thing is an artificial number. That's the sum of the 500 computers. So that's an Excel sheet computation. Add up the performance that the 500 computers get, and we're about a little over half an exaflop today, half an exaflop. So there's many, many interesting things that come out of that list. So the slope of the line, Moore's law says it should double every 18 months, transistors. So what do you think the slope of this line is? So the slope here is doubling every 14 months. So it's accelerating Moore's law. So why would it accelerate Moore's law? Algorithms, same algorithm. That's one of the nice things about this. We're not changing the algorithm. You could say optimization then. Optimization plays a role, but parallel processing is the thing. So more processors on each of the machines that every time it comes out. You know, the guy at the bottom of the list today, that was equal to the sum of all the machines in 2001. 2001, so that's a short period for that to take place. You know, these machines at the top are very expensive. The cost is about $200 million US. That's for one machine. And you got to realize that after 6 years, that machine is no longer a supercomputer. So you got to make an investment again. So this is it's a costly thing to be involved in high performance computing if you're going to be number one. And you know, the stunning thing here, so this laptop here is incredible. So this is a dual socket Intel Haswell processor. I can run the benchmark on it. And when I run the benchmark, I get 70 gigaflops out of my laptop. 70 gigaflops. That's a laptop I use to read email. Right? That's stunning, incredible. You know, the changes that are occurring here. And you know, that would have been on the top 500 list. In fact, it would have been faster than the #1 machine. The #1 machine was a thinking machines, a CM5 with 1,000 processors used at Los Alamos National Laboratory to carry out, you know, classified things to design weapons. That's an incredible situation we have today. Amazing. Okay, so my phone. So I can run the benchmark on my phone. There's an app for that. You can download it and run it. It's free. And you know, I get 4 gigaflops out of my phone. That's stunning. And that would have been on the top 500 list. So 4 gigaflops, you may not know this machine, but a Cray 2 was 4 gigaflops. A Cray 2 was 4 gigaflops. That's amazing. I wear it on my belt. It has a battery that lasts 24 hours. That's stunning. Okay, and then this is a projection of where things might be going. So we're looking at here the #1 machine and projecting out. It's on a log scale, so you got to be a little bit careful. So we had a teraflop in 1997. 11 years later, we had a petaflop computer in 2008. And the projection here would say that we're going to get to an exaflop, 10 to the 18 floating point operations in 2020. In the US is saying we're going to get to an exaflop in 2023. The Chinese say we're going to get there in 2020. So I'm betting on the Chinese right now. They're going to get there in 2020. Okay, so today, if you take a look at these 500 computers, we have 95 machines which are running at petaflops or greater, 95. So about 20% of the machines are at 10 to the 15 or greater. We see 3 technologies there that are being used to build these machines. So one technology says we're going to use commodity processors. Take Intel parts and put them in a box, connect them with some interconnect, and that's going to be our supercomputer. So that's a path that we have today for high-performance computing. The second path is to take those commodity processors and use an accelerator, like a GPU, to make it run faster. And that's another path that people use to, again, boost the performance of their systems. And there are 93 computers which use accelerators today. Again, about 20%. And then there's this lightweight core thing. So we're seeing machines that are being designed using a processor which doesn't have all the sophistication of the Intel processor, the Intel Xeon processor. Intel Xeon processor is a complicated processor. It does all sorts of important things for you, look-ahead instructions, prefetching things, has cache that's very sophisticated. And all that comes with a price. And that price is usually power that's burned to get that stuff. So we're seeing lightweight cores that don't have some of those things. So the new Chinese processor from Shenwei is a lightweight core. There's no cache on the processors. Right? It has very few look-ahead things. ARM processor. So ARM is the thing that's in our phones. That's a lightweight processor. ARM was just sold to a Japanese company for $32 billion. SoftBank bought ARM architecture. So that's sort of an interesting investment. The new Fujitsu computer, supercomputer, will use ARM processors. And one of the new Chinese machines will use ARM processors. ARM's about to make an announcement next month about their supercomputer chip, supercomputer architecture. And Intel has something which is a lightweight core called Intel's Knights Landing. It's the new Xeon 5 processor. And we'll talk about that in a moment. We see interest in high-performance computing. If you take a look at this list of the 500 computers, about half of them are used in industry. Not in research, not in academic setting, but in industry. So industry sort of gets this. It provides some kind of strategic advantage for the company to use high-performance machines. They get some boost in terms of what they're doing over their competitors. And we see a number of projects that are looking towards exaflop computing in many regions and countries. And here's a striking thing. Intel processors, if you take a look at these 500 computers, Intel is used in 91% of those computers. So x86 architecture from Intel is used in 91, and then AMD has another 3%, which is x86. So 94% use that instruction set. I find that just incredible. Again, at one time there was a business of companies that just made supercomputers, and today that's gone away. And that's gone away. Intel processors has saturated that market. Okay, so here's the 500. Here's a representation of the top 500 list. This is a graph which shows 500 rectangles. Each rectangle represents a supercomputer. The area of the rectangle represents the power of that supercomputer, the speed of it. So this is the biggest one here in China. And this is the number 2 computer in China. And this is the number 3 computer. If you take a look at the list, China has 167 of the 500 computers. And the US has 165. That's the first time that's ever happened, that the US is number 2. US has had more than half of the machines for a long, long time. So that's a stunning achievement. Japan, 29, Germany, 26, France has 18 of these machines. We'll take a look at that in more detail, and so on and so forth down the list. And China has a third, and the US has a third. So here's the top 10 computers. So this is number 1. This is a machine at the National Supercomputing Center in Wuxi. So it's called the Sunway Tianhe Lite. It uses their own processor. This is a processor that was designed, fabricated, and built in China. It has their own instruction set. It has 260 cores, and it uses a custom interconnect. So the way in which the processors talk to each other is through something they built. This is totally Chinese in design. And it has 10 million cores, 10 million cores. So if you're going to program this machine at scale, you have to coordinate something on the order of 10 million cores dealing with that. That's an incredible thing. The benchmark ran at 93 petaflops. 93 petaflops, and that's 74% of the theoretical peak performance. So they left roughly 25% on the floor, right? But they used the machine at scale, so they used 10 million cores to do this. And that was 15 megawatts. That's the power consumed. That includes only the memory, the CPU, and the interconnect. It does not include the cooling. Cooling's another 20 or 30%. of the power. In the US, 1 megawatt year, if I did that, if I used 1 megawatt for 1 year, I get a bill for $1 million. So it's a megawatt year is $1 million. So that machine, I don't know what power cost in China, it's about $15 million to turn it on, right? So it's an expensive deal, high performance computing. Okay, you can go down the list here. This is the number 2 machine, the Tianhe 2. It was built by the National University for Defense Technology. They were integrators. They took parts from Intel, they built their own interconnect, and they put together a machine. And it has only 3 million cores in that machine. Again, they got 33%, roughly a third of the performance of the number 1 machine. In fact, that number 1 machine, you have to add up 6 of these guys to get more than it. That's an incredibly powerful system. And you could see the power consumption and the peak performance here for the various machines. So cores are a lot of cores in these machines. Power is a big deal for high performance computing. And we see accelerators being used in these machines. So 3 of the 10 machines use accelerators, this Xeon Phi, this GPU from NVIDIA. And we see those 3 different architectures here. So there's a number of machines here, like this one, that just uses commodity processors, and this one, and this one. So those are just using commodity processors with some custom interconnect making that machine. And then we see machines that use lightweight cores. So the Sunway machine is a lightweight core. The Blue Gene, IBM Blue Gene. So IBM used to be in the business of building this high-performance machine, and they were very successful with it in terms of a machine which worked very well, but they decided to stop making that machine because it wasn't profitable. It wasn't getting them what they wanted. And we see China having a few machines. US has 4. Japan 1, Swiss, Germany, and Saudi Arabia round out the top 10 machines on that list. And again, the situation, if you take a look at number of machines over time, China had 0 machines in 2001, 0 computers on this list, and they've made a big investment in high-performance computing today to get to that point. And if you look at the aggregate performance, the US is here, the EU countries are here, and you see China's increase. So today it has more computing power, let's call it, than the US. Here are the machines in Germany, in France. So there are 18 machines here, and I think 12 of them use Bull computers that are integrated by a French company. Right? Not surprising in that sense. And you can see which companies have which machines. This machine is ranked number 11 at Total. The Meteo has a couple machines on the list, and EDF and so forth. And CEA is a big proponent of high performance computing as well. Okay, so we talked about accelerators, and it presents a hybrid design. So it's hybrid in the sense you're putting together different kind of computing devices, and you have to write programs for each of those devices. So you have to write a program for the host, and you have to write a program for the GPU as well. And that has some issues associated with optimizing and getting good performance over it. But and we've seen the number of accelerators increasing. So today, 93 systems use accelerators. NVIDIA is the guy who has the most accelerators being sold. Xeon Phi comes in second, and the last one is AMD with its ATI card. And the performance for the accelerators is about a third of the top 500 aggregate performance. That's one way to look at it. It's come down recently, mainly because of that big Chinese machine, which boosts the performance, and it's not based on an accelerator, so the accelerator portion goes down as a result of that. So here's the way it sort of works, this accelerator hybrid design. So you got a host processor here that's in control of things. So there's a multi-core chip that's in control. It has some memory, and then next to it is this accelerator. And this accelerator I've used is a Xeon Phi. It's the new Knight's Landing Xeon Phi. So there's a link here between these two guys. And that link is the link through memory. So this guy here is running a program, and that program wants this guy to help out. So what it does is it sends information from the host memory over to the accelerator, to the GPU, stores it in its memory, and then issues an instruction that this accelerator should do something with that data. So it does some operation. The host processor goes off and does something else asynchronously, and later comes back to see if, in fact, that guy's finished. If it's finished, then it comes back and gets that data. So the problem here, this accelerator is quite powerful. It's at 3 teraflops. This host processor here has a performance which is about maybe 100 gigaflops. So a big difference there. You get a tremendous boost if you could use this thing. But the problem here is you got to communicate over this pipe here. You got to pass information across this link. This link is the speed of about 1 gigaword per second. 1 gigaword per second. Words are 64 bits. And the performance here is at 3 teraflops. So if you pass something across this link here, you better get a lot of operations out of it. You better do a lot of work on that data, because that link costs a lot. Passing that data across that link is a very expensive endeavor. So you want to be able to pass data over there, do a lot of operations, and then pass the information back. If you pass a small bit of information and then do some operation and then pass it back, you're going to be killed in terms of the performance of that link. So you want to do something like a matrix multiply or an FFT over there. Small data, getting a lot of work out of it. You pass n squared pieces of data and you get n cubed operations. That would be an ideal way of doing business. So that has a problem here. Now that's going to change in the next design. The next design, things always get better, right, over time. Things always get better. Intel, with its Knight's Landing, is now freeing up this chip. So it's no longer an attached thing, it's its own thing. It's self-hosted, is what they say, self-hosted. So it can be its own processor. It has 72 cores. They're running x86 architecture. So anything that you ran on your old machine can run on this machine. 72 cores share memory in this context. The memory here, some of it's on the package. So this memory that's on here, so this is 72 cores, and they have 8 of these MCDRAMs. MCDRAMs are stacked memory, 3D memory. So in the old days, memory was linear, 2-dimensional. Today, we're stacking memory. So we're doing it, and think of a tower of memory. And now the chance of passing data is, the data rates get enhanced because you're stacking it. Data rates flow, the data rates are able to go horizontally through the memory, and you get much better speed associated with it. So this guy here has, each of these things here are 16 gigabytes of memory, and that memory aggregate speed is at 500 gigabytes per second, so very high rates of data movement from this memory into these cores here, and that's on package. That's sitting there next to the processors. So that's a very impressive arrangement that we have. This is the Knight's Landing, and that's a self-hosted thing. You can buy, pretty soon you'll be able to buy machines which have that chip on it and associated with it. So things are getting better. It's no longer an accelerator. Okay, so this is the processor that the Chinese have built. If you're interested, there's a report that talks about this machine in a lot more detail. So they built a chip. It has 260 cores on it. And again, it was fab designed and has its own instruction set. It runs at 1.45 gigahertz. So that's a very modest cycle time. The chip itself has 4 core groups. Each of these core groups are made up of a mesh of 8 by 8 cores, 8 by 8 cores, and then 1 controlling core. So in some sense, think of it this way. If you're writing a program, that controlling core is going to be the MPI process. And it's going to hand off information to this cluster of 8 by 8 to do the work. And the programming model they're using is OpenACC. So OpenACC is being called to do the work across this, cluster of things. So this is a chip. So there's 4 of these controlling processes, or 4, think of them as MPI processes on this chip. It has a network on chip that connects things. Each of these guys here have some memory associated with it. It's a small amount, 8 gigabytes of memory for each of these clusters. And there's a link out here, a PCI Express, which connects into the network. That connects that so that this guy can talk to other guys in the network. So this chip here is 3 teraflops. So that's the peak rate for that chip. 1 chip, 3 teraflops. And what they do is they build, they put together a board which has a number of chips on them. They put together a cabinet which has 1,000 of those chips in it, 1,000 chips in a cabinet. That cabinet is about 3 petaflops of performance. And the whole system has 40 cabinets in the room. So 40 cabinets fill up a room. 4,000 of these nodes, each node is a chip. 125 petaflops is the theoretical peak performance for it. And 10,000 cores. It has 1.3 petabytes of memory. So the memory that's being used here is old memory, DDR3 memory. So it's slow memory. It's cheap. It's slow. It doesn't use as much power. That's one reason why the power for this machine is low. They use slow memory. They have a slow cycle time. And LINPACK, when you run it, it gets 93 petaflops, and that's 74% of the theoretical peak performance. Now we have another benchmark, and that benchmark is solving a linear system of equations as well, but it uses an iterative method. It uses the conjugate gradient method. So think of it as a separate benchmark running that does an iterative method, and we're going to look at the performance for that iterative method, implemented on your machine using the best optimization you can for that iterative method. The problem is it comes from a partial differential equation. It's a 27-point stencil. It's a 3D problem. So the benchmark, HPCG, that runs gets 0.32 petaflops, 0.32 petaflops compared to 93. They're using the whole machine again to solve that problem. LINPACK gets 74% of theoretical peak. This one gets 0.3% of theoretical peak. 0.3%. So that's a very low number, right? So if you're going to implement an iterative method on this machine, you're going to have a hard time extracting performance from this architecture. And that's because of the data movement problems. You've got slow memory associated with this. Right? So this machine has 15 megawatts. This machine has an efficiency of 6 gigaflops per watt. So you want that number to be as high as possible, 6 gigaflops per watt. That's a very good number, by the way. Normally, the supercomputers we have run at 2 gigaflops per watt. 2 gigaflops. So it's, again, getting a very high performance, although it has some of these other limitations. At the big supercomputing meeting in November, we have this prize that's given out. It's called the Gordon Bell Prize. Gordon Bell is this legendary guy in computer science. He wanted to encourage the use of parallel computing. So he donated a few $1 million to endow a prize. And the prize gives out $10 million a year. So $10 million is given to the winner of this prize, and the winner is the paper that shows an application being implemented on a parallel computer that gets better performance than the previous year. Okay, so that's sort of the ground rules for this. And there's a committee that looks at these papers and makes decisions about what goes forward. People submit a paper. They say they want to be a Gordon Bell finalist. The committee picks 6 papers, And those 6 papers go forward for the finalists, and then they'll ultimately make a decision and announce the decision at the big supercomputing meeting. The Chinese, on this computer, submitted 5 papers for the Gordon Bell Prize, and 3 of them became finalists. So they have half of the Gordon Bell Prize entries. Right? So it'll be interesting to see who wins. This machine cost 1.8 billion RMBs, so that's about $270 million. In the US, we think about $200 million as the cost of the machine. That $270 million includes the cost of the building. It includes the research that went into building the applications. It includes the compiler, the time it costs to build the compilers, all the software stack, everything. So that's all in the $270 billion. So that's a pretty impressive, and this is sort of the layout of the machine. So there's 20 cabinets in each of these zeros. And this is the cartoon they put together that show a board with 2 chips on it. This board is put onto another board which has 4 boards on it, 2 up and 2 down. This is a water-cooled machine. The water is flowing into this metal thing here. The chips are in contact with that metal to cool it. They stick a bunch of boards, 32 of them, into a sub-rack, and that rack then gets put into a cabinet, and then that cabinet fills up a room. Right? So then they fill up a room with this thing, and that's their computer. Yeah.
So you said that it was very well cooled, so it doesn't allow to get a better frequency?
So it is cooled, and that's the frequency that they have to run at. So 1.45 gigahertz is the frequency. They can't do better. So in order to do better, you could think about using some kind of a fancy cooling. So if you can cool the machine, you can run at a higher frequency, because then you can dissipate the heat and do better. So people have tried immersing their machine in oil as a cooling method. Oil's a better conductor. People have thought about immersing their machine in some floor inert, and some liquid, to some very specialized liquid to remove the heat. Some people have put their thing in a supercooled machine, liquid nitrogen. So we've seen machines put in there, all to try to get away the heat. This machine is done very simply. It's done using water. The water is recycled. They could run it faster, I guess, if they use some more exotic cooling, but they choose not to. They choose to use something as these chips heat up too, the life of the chip declines as well. So there's all sorts of issues that have to be considered for things like that. Okay, in the packet there's all sorts of supercomputers. We're not going to spend time going through this. This is sort of interesting and boring in a way. So this is the customer segment. These are the breakdown over time of how the supercomputers are, in what industry they're used in. And are they used in research? That's this blue. Are they used in an academic setting? That's this pink. Or are they used in industry? So again, industry has a large share of high-performance machines, which is sort of interesting. And it's across all sorts of areas that people are using the high-performance machines. Multi-core is here. We think about these cores as being the same, but we're starting to see designs which look at different kinds of cores. Think of them as lightweight and heavyweight cores. The Chinese machine has this kind of design. They have lightweight cores, and that 8x8 mesh, those are very lightweight cores. And then they have a controlling processor, which has the same instruction set, but uses a much more sophisticated way to do business. The controlling core on that machine has cache. It has some look-ahead features and can do what we would consider more advanced architectures. So we would think that perhaps this is a way forward. I mentioned the stacking of memory being an important thing, and it's going to become more important. You think about getting information into a chip. It's limited by the pins. That's the perimeter of the chip, essentially. And if you could think of stacking things, stacking memory, you'd have much greater bandwidth to get that into the processor. Today, the memory is stacked next to the processor. That's what we see on the Knight's Landing. Future designs will have that stacked on top of the processor. So information will flow directly into the processor rather than to have to go in around on the pins themselves. So that's coming. And we would see machines which would have, perhaps in the future, thin cores and fat cores associated with them. We would have 3D stacked memory that was on chip. Off chip, there would be conventional, let's call it DRAM. And then what we're seeing today is non-volatile RAM being put into machines, non-volatile RAM, so it saves state. If the machine goes off, it saves its state, so you don't lose the information. And that will be used for doing checkpoint and restart is the goal. So if the machine, today if a machine falls over, if you lose a process today, an MPI process, you lose one of the cores in your 10 million core machine. If you lose one of the cores, your application is going to fall over. MPI has no way to recover. There's no fault tolerance built into it. So the standard way we think of recovering from an error, a fault, is to do a checkpoint. And the checkpoint is to write stuff off today to secondary storage. That's an expensive thing, writing off petabytes of data to secondary storage. So this NVRAM will be used to write off information, and when we lose something, we can get back the information because it hasn't gone away. Think of NVRAM similar to your USB stick, although it's a lot safer than your USB stick. Can be rewritten many more times than that. So that's a design that we're seeing in our architectures today, again, with the thought of being able to recover in some very quick way from a failure that occurs within our complex, either software or hardware failure that takes it down. And beyond that, we're looking at stacking things on the chip itself. So three-dimensional fabrics are coming into play, and the copper that's used to pass information, that's going to go away in some future design. So it'll be optical, and then things get a lot faster too. And also the heat goes down as a result of that connection. So sometime in the next, let's say 10 years, we would start to see these kind of things coming into play and being available for processors. Okay, so we've got Moore's Law, doubling the number of gates on the chip. For us, it's a matter of increasing the number of tasks that we have. The number of threads of execution that we have is the thing that's going up in some way that somehow has to be managed, and that's going to be an important thing. Okay, I want to move on to the linear algebra part here and talk about some algorithms and look at some issues that we have. We're going to be talking about sort of standard stuff. In my context, I'm going to be talking about dense problems. And dense problems do arise, and they are being handled. They come about by radar cross-sectioning, flow around chips, the diffusion, noise reduction, and a number of other things. So they do play an important part in our story. There's a web page that I sort of maintain, which has a list of what I call freely available software. So if you're interested in linear algebra software, both for dense and sparse problems, there's a list of packages that people have developed over time. Some of those packages are maintained on an ongoing basis. Others are not. This happens to list the dense direct solvers, but the page goes on to list sparse direct solvers and sparse iterative solvers. That's the web page that you can go to find it. And I've tried to put a link in. The link most likely is active. Look at the licensing that software can be used under. Look at the support, if any, comes with it, and how it works in real or complex arithmetic, what languages are supported, if it does distributed shared memory, if it accommodates for accelerators. So if you're looking for something and you're not quite sure what you want to look at, take a look at that web page, and that might help. That might help with you. Yeah.
Is
on the right over here. So M means message passing using MPI, and C means CUDA. I think it's CUDA, and I can't remember what O means. OpenCL, thank you. Yes, I can't remember what X means. If you go to the web page, you'll find out. So it's there. Yes. So we tried to do that, and we did this for all the packages, and we tried to engage the authors of the package as much as possible. So it provides a handy source, perhaps. And every 2 years or so, I update it and make sure the links are still valid. Okay, so we're interested in this. I've been involved in software for a long time. This is sort of, if you will, a slide that has my whole life story on it. So I've been involved in doing this for about 40 years. In the beginning, there were algol routines that came from this book by Wilkinson and Reinsch. So they put together the state-of-the-art of algorithms for solving eigenvalue problems. And they were written in algol. Those algol routines were good at the time. There was a project called IcePack that was put together in the 70s. IcePack was intended to take the algorithms in this book and to convert them to Fortran. So Fortran was the language that was being used. Algol wasn't really getting much traction in the US, and it was thought that these were good algorithms and they should be implemented. So IcePack was created. It was Fortran code. The guys who did the software here, they knew something about optimization, and algol stored things by row. So the algol routines access the information by row. The IcePack crew were going to faithfully translate the algol into Fortran. So faithfully, they translated the row orientation into row-oriented Fortran code. And as we know, Fortran stores things by column. So it has a major impact in terms of performance, right? So with cache systems today, we access one element, and we get its buddies for free. Its buddies are the guys next to it. And if in Fortran they're stored by column, I get a chunk of the column. But the IcePack routines are looking at row accesses, so they're causing lots of cache faults to occur. So that was the problem, let's call it, with IcePack. IcePack was a wonderful package. It was exploring portability. Portability, trying to get the same piece of software to run on all these machines in an age when we didn't have IEEE arithmetic. So there was a major challenge at that point to do that. That was a very successful effort, mainly eigenvalue software in that package. And that was in the 70s. Then came a project to take on looking at making a portable version for linear systems of equations. So that was LinPack in the 80s. We had vector machines, and we knew about orienting things in Fortran by column. So LinPack was organized to access things by column and to use vector operations. So we had level 1 BLAS. That's all we had. That's all that was created at that point. And that's the story of LinPack. And we know, of course, that we want to do more than vectors, and I'll explain that in a moment. And in the 90s, we had systems which were cache-friendly. They did have cache, and if you use the cache effectively, you get very high rates of execution. So we took the job of taking these two packages and rewriting them to be blocked and cache-friendly, trying to organize things around these level 2 and level 3 BLAS operations that we had created to effectively use them. And in the 90s, LAPACK was created. After that, message passing came into play. So we rewrote all of that software to do message passing, to do sends and receives explicitly using MPI. So that was ScalaPack. And today we see that in order to effectively use the architectures that we have, if we want to be able to scale to the rates, to the numbers of processes that we see on the machines today, we have to change the design. The basic problem is these algorithms here do a fork join kind of parallelism. They fork something off to do parallel processing, and then they join together to do something sequential. If you have 10 million cores, you can't wait for that sequential thread to finish. You're wasting 10 million cores are sitting around idle. So you have to do something different. So the design of these packages today are looking at much more structured design, expressing the algorithm not in terms of fork-join parallelism, but in terms of a directed acyclic graph, much more data flow in nature. And I'll talk some about that. That's something called Plasma, and in the other software that comes from that is being reorganized and redesigned today to effectively accommodate the architectures. But I want to talk about Intel and what Intel is doing to us. So this is sort of a story, a history of Intel Xeon processors. Intel Xeon processors are pretty impressive. In the early days, a Xeon processor did 2 per core, did 2 floating point operations in double precision in the early days. In 2009, with Nehalem and Westmere, they doubled that. They gave you 4 floating point operations per core. With Sandy Bridge in 2011, we got to 8 floating point operations per core. Per core, 8 floating point operations can complete per cycle. With Haswell, you get 16. So that laptop gets 16 floating point operations per core. That's a stunning achievement. That's the completion rate, 16. And with the new stuff, this is Knight's Landing, Intel's Xeon Phi, the new Xeon Phi processor. It does 32 floating point operations per cycle per core, and they've got 72 cores in that thing. So that's an incredible floating point rate that's coming out of this thing. These machines have been over-provisioned for floating point, right? It's incredible. And the question is, can we effectively use that floating point execution speed? So here's a little model that I want to go through. So this is my laptop. So this is a model of my laptop. It has CPUs, has 2 cores, actually. It has some cache, 6 megabytes of cache. It has some memory, 8 gigabytes of memory. And I can move data from memory up to the cache at this rate, 25 gigabytes per second. That's the data transfer rate on that laptop. And so it's an Intel Core i7. It's a Haswell processor, 2.3 gigahertz. That's the rated cycle time for that processor, 2.3 gigahertz. But it has something called Turbo Boost. So Turbo Boost is something that can kick in depending on the conditions going on in the chip. And when that kicks in, I get 50% more cycle time. So the cycle time can be boosted to 3.5 gigahertz. I don't have to do anything. It just happens, 3.5 gigahertz. And when I run stuff on there, in most cases, I get 3.5 gigahertz. That's the cycle time I run at. So 16 flops per cycle. That's what this guy can produce, 16 floating point operations per cycle. 16 double precision floating point operations per cycle. At 3.5 gigahertz, says that I get 50, the potential is for 56 gigaflops out of 1 core of that laptop. Right? That's stunning. So that's sort of, I want to analyze this model. So the model is cache, some transfer rate, and some rate of execution that I can do here with this particular processor. So let's say I do a vector operation on this computer. Some simple thing like a dot product or a DAXB. So a dot product, we're going to take 2 vectors. We're going to multiply them component-wise and add the results. With an AXB, we're going to take some scalar times x, add it to another vector, and store the results. So each of those operations, I'm going to be doing 2n floating point operations associated with it. And I've got 2 vectors that I have to read. 2 vectors I have to read. In this case, I have to write 1 vector. Write 1 vector. And now I want to see what the performance is going to be on my laptop for this operation. And what I want to do is to remove issues about latency. So I'm going to make vectors as large as I can. So the vector I'm going to take is a vector of length 375,000. So I've got vectors of that length to fill up cache. So basically, I'm going to read them into cache, do the operation, and then see what kind of performance I get. So the data size is 375,000 double words, so 8 bytes double. That gives me 3 megabytes per vector, 3 megabytes per vector. I've got 2 vectors, so that fills up cache exactly with 6 megabytes. That's the cache size on this machine. So the time it takes to move those vectors, those 2 vectors, into cache is going to be at this rate, 25.6 gigabytes. So I'm moving 6 bytes, 6 megabytes, so the time is 0.23 milliseconds. So that's the time to transfer the data into cache, right? And then I'm going to do the floating point operations. And the time to do the floating point operations, I've got 2n floating point operations at 56 gigaflops. So the time is going to be 0.01 milliseconds. So the time is insignificant compared to the time to move the data, right? So moving the data took all the time. And if I think about overlapping floating point and moving the data, you could do that in some cases. So let's take the minimum, or sorry, the maximum of those 2 numbers. So that gives me this number here. So that says at that rate, at that number of flops, it says the dot product will run at less than 3.2 gigaflops. So I'm going to get 3.2 or less gigaflops, the rate of execution out of that machine. The peak is 56. So now I'm running, this is communication bound, right? I have no hope of getting high performance. If I do vector operations, I'm dead in terms of performance. Let's go up the hierarchy. Let's say, let's do something more than vector. Let's do a matrix times vector. Let's do that one next, matrix times vector. I've got 2 n squared floating point operations and n squared pieces of data have to be moved. So I get a slightly better ratio. Here the ratio was 1. Operations to flops, operations for data movement is 1. I got 2n flops and 2n memory references, so that gives me a ratio of 1. Here I've got 2n squared flops and n squared movement, so that gives me a ratio of 2. Okay, so let's go through the same thing. I'm going to make things so that they fit in cache. So the matrix is going to be of size 860. 860 squared double precision words plus a couple of vectors makes me just about 6 megabytes. That's the size of cache. So I read in that data. I do the floating point operations. The time to read in that information is the same. I'm reading in 6 megabytes, so it's 0.23 milliseconds. The time to do the floating point operations now is 0.26 milliseconds. So now it's taking a little bit more time to do the floating point work. And remember, we're going to take the maximum of these 2. We're going to overlap them. So the time it takes to do this operation is 0.26 milliseconds. And if you do the computation here, doing this number of flops, it ends up at 5.7 gigaflops. So the rate has gone up. I got better than 3.2, but I'm nowhere near the 56. So if I do a matrix times vector operation on this machine, I'm going to be dead in terms of performance. I'm going to get nowhere near the potential performance for this architecture. So again, we're communication bound for a matrix times vector. Okay, so let's go again. Let's look at doing a matrix-matrix operation. So I'm going to take 2 matrices, multiply them together, and add it to another matrix. I size things so I fill up cache again to I don't have to worry about the latency issue. So now I've got 3 matrices of size 500. So 500 by 500 matrices are read into that cache, fits cache perfectly. And I get the time to move the data is the same, 0.23 milliseconds. And the time to do the floating point operations now is much more substantial. I get 4.46 milliseconds to do the floating point work. So now I'm in a situation where I can get, again, if I think about overlapping the operations, it takes 4.46 to do this. I'm doing this number of floating point operations. So that translates into 53 gigaflops is the potential for this machine. 53 gigaflops is getting very close to the theoretical peak performance for the machine, much greater than the dot product or the matrix times vector product. So I have the chance of getting that high performance. So when I run the experiment on my laptop, this is what I get. This is a vector operation. For large vectors, I get 1.6 gigaflops for doing vector operations. I get 3.4 gigaflops for doing a matrix times vector operation. And for matrix-matrix operations, I'm able to achieve something close to 54 gigaflops. So that's clearly where I have to be if I'm going to think about extracting performance from this architecture. Anything less is going to be leaving a lot on the floor in terms of performance. So that's sort of a key thing in terms of algorithm design, trying to design things at a level which you can effectively get high performance. And when you think about moving data, it takes an incredible amount of time to move that data. So if I think about an access to main memory from DRAM, it takes 167 cycles to move a piece of information from DRAM through the memory hierarchy to the point in the machine where I can effectively use it. 167 cycles. So if I don't get if I don't get access, if I don't get reuse of that data, I will have wasted essentially a tremendous amount of time just loading the information. And here's the time for other accesses. In that 167 cycles it took to get that memory, to get that data from memory, I could have done roughly 2,500 floating point operations. And the amount of time it takes to do this roughly translates into the amount of energy needed to do that operation. So the amount of energy to do a floating point operation is measured in picojoules. To do a floating point, 64-bit floating point operation is roughly 20 picojoules in terms of the energy needed to carry out that operation. And the energy to move the data is something that's measured in terms of nanojoules. So again, we've got 3 orders of magnitude difference between those two quantities. So data movement is going to be the thing that will kill the performance from our algorithms, and it's something that we have to be quite aware of. I have to say that this is a picture of different processors looking at the rate at which we can do floating point operations and the rate at which we can transfer information from memory. So think of it like this. I'm going to do floating point operations. How much does it cost to move the data? In the old days, that number used to be 1. The ratio was 1. 1 floating point operation, and I would move one word of information. All right, so that's down in this range here. In the old days, computers were designed to get that kind of performance. 1 flop per 1 word from memory. In the old days, floating point was very expensive. Today, floating point is over-provisioned in our hardware. These machines that we had here in the old days were good for many kinds of operations. They were good for vector operations. They were good for sparse matrix computations. Today, the architectures that we have at this range here, that's where we're sitting today. They get a ratio that's above 10. These machines here are good for doing matrix multiply, basically, at very high rates of execution. And for the other operations, for sparse kinds of operations, we end up really at sub performance for those. So I think I'm going to stop here and we're going to take a break, but let me ask if there's any questions before we do. We have time for a few questions. Yes, Martin?
Are some of the computers on this top 500 list especially designed to win this competition, which means the queue for this Gaussian elimination benchmark?
So that's a very good point. So do people design computers to be number 1? Do we want to have the trophy on our mantle? So I would say that perhaps the design point for some machines are such that they do LinPack good. They do LinPack good, which means they do matrix multiply very well. And as a result, they may not do any other kinds of computations. They may fall in terms of the other computations. That's right. So that's the fault of the benchmark, let's say. Right? So over time, that benchmark has become important to the point where people design machines around the benchmark. So that's a bad thing, and we don't want to have that happening. So people recognize that, and it's good. You know, we've always said it's good to look at other things in trying to measure the machine. But because that benchmark has such a great impact because of the list of the top 500, maybe that's an issue that has to be corrected. So we're trying to correct that. We have this new benchmark called the HPCG benchmark, the conjugate gradient benchmark. Other people have other benchmarks that I think are exposing other facets of the machine, which is good. And you know, we need to drive computer vendors in the direction of optimizing for these other things to help us in terms of the computations that we really need to do. So I think that would be a good thing.
So we've had Stream for 20 years. Does HPCG tell you anything that Stream doesn't tell you?
So Stream is a benchmark which just measures the rate at which we move information from memory. So it's basically no floating point operations. It just moves data from memory. And we've had that for a long time. And so that's an interesting benchmark to look at. How fast can you move information? And I would say if you naively implement HPCG, then it would look like Stream benchmark. But if you take some effort in terms of optimizing it for the capabilities that it has, then it doesn't look like Stream. So it's almost like anything. Anything naively implemented will behave like a data movement problem, straight like a data movement problem.
It's a completely data limited operation, one.
Stream is.
CG is.
HPCG does have floating point associated with it.
But it's completely limited by the memory transfer.
Memory transfers dominate the calculation.
More than 5% of peak on anything that you run.
So there's examples where it's getting 10%. Right. So I would say that it's limited at that rate. That we won't see high rates of execution clearly from that, and it'll shine a spotlight on things that perhaps should be enhanced, let's call it, in future designs. And I think that's really what's needed here is to get vendors to stop giving us more floating point operations per cycle in our cores and giving us more data movement associated with that to enhance the computational rates for real applications.
And it won't tell us about latency, right?
Well, we have latency numbers coming out of our HPCG benchmark, so it does give us some information.
Part of it is sensitive to latency?
We monitor what's going on in some basic operations and look at the latency associated with those operations, as well as the rates of execution.
So you're telling me like the dot products?
Dot products and things like that, yeah.
All right.
That's right. Yeah. So there are a number of facets that benchmark pushes on. It doesn't push on everything as it possibly can't. There are alternatives to that benchmark, which should be looked at, I would say. One-stop shopping doesn't buy everything, and that would be another way of looking at performance.
Other questions?
Yes.
At some point you say that this Chinese machine does not have any in-core cache memory.
So the basic clusters don't have cache memory. They have scratchpad memory. So they have a small amount of scratchpad memory, 64K bytes of scratchpad for the whole computational cluster. So that's user-managed. That's a user-managed cache, if you will. It's a small amount of user-managed cache. So there's no cache in the way we conventionally think of cache on that cluster, though. So it does possess a little bit of memory to store things.
So you have to manage it by hand somehow, so in order to increase the memory transfer.
Correct. You have to do that. I haven't been able to look at actual programs and understood how the optimization is done at a very detailed level. They're using OpenACC again to get access to the floating point capability of that computational cluster. It'd be interesting to see exactly what they had to do to get performance out of it. It's another design point for hardware, is the way to look at that. That machine was clearly designed to be number one, and it's number one by a lot today. So it's probably not a well-balanced machine, is the point of that.
Yes, you said that NVIDIA GPU card can be seen as a 14 cores processor.
Yep.
Is it possible to use them like this? I mean, like it would be on a standard computer?
So things are not quite the same as on a standard computer, but that's the way you could think of programming it. 14 independent streams that could take place on that device to do something. So it is a way of using it. So we needed a way to talk about cores in a common setting. So you can't talk about 2,644 CUDA cores and count that as the number of cores on a device. That would be an extreme way of doing it and unfair to regular cores. So when you take a look at the NVIDIA arrangement, you're able to stream instructions from an instruction stream in just that way. So they have 14 of those instruction streams there that are possible, independent instruction streams possible.
If there are no more questions, it's perfect timing, so let's thank Jack. And we have a break until 11.
Okay, so let me just start up again. We ended the discussion that we had talking a little bit about computers that are built specifically to do the benchmark well, or to do high on the top 500 list. So this is looking at a few computers from the top 500 list. The blue dot here represents the theoretical peak performance. So that's the upper limit for the machine. And the red dot is the LINPACK number. So that's the number they achieved on the top 500 results. And I mentioned this new benchmark we have, HPCG. HPCG is doing conjugate gradient. So it's a sparse matrix vector multiplication, sort of driving things, vector operations, very data intensive things going on. And when we look at the performance for that, this is the performance we see for those machines. So there's a big drop in performance. That drop goes from getting close to the peak performance to something which is now getting about 1 or 2% of the theoretical peak performance for the machine for doing this kind of computation. If you take a look at the machine, so this is the top 10 on the new benchmark, HPCG. So this is the number 1 machine. It's the number. It was the number 2 machine on the other list. It's the Tianhe 2. It's the machine with Intel parts, and this is the percent of peak it gets. So it gets 1.1% of the theoretical peak, 1.1%, and it achieves 0.58 petaflops. That's its execution rate for solving the CG benchmark. And you could see the difference going down the list here. So the number 2 machine is the machine in Japan called the K computer. The K computer was a special design machine, designed for high performance computing. Has very good data movement within the machine, does very good balance between floating point and data movement, and it gets about 5% of the theoretical peak. So that's a machine which is was designed in some sense for scientific computing, getting around 5% of theoretical peak. And it's, the number one machine is at 0.3%, and you see the other machines down the list here, the top 10 anyway, somewhere between 5% and 0.3% of the theoretical peak. So again, matrix multiply, you can do very well on these machines. Anything else that has data movement associated with it, you're going to see the performance drop in a very precipitous way. Okay, let's go back to the story. We're going to look at some dense matrix calculations. This is a cartoon of what we did back in the 70s. So in the 70s, LinPack was designed. LinPack was column-oriented, respecting Fortran. And for the factorizations, it basically looked at the factorizations, and what it tried to do was to introduce zeros down this column of the matrix. So it introduced zeros and changed this column. The next thing it did is to update the rest of this matrix. So it introduced zeros and then applied that transformation that introduced those zeros to the rest of the matrix, updating a tremendous amount of data. A tremendous amount of data was updated in this algorithm. And it suffers in terms of performance on today's machines because of that. It has other problems associated with it. It is doing partial pivoting to make things stable along the way. It does this, what I call bulk synchronous processing, fork join processing to effectively do business. And that's going to cause some issues down the line. It did a lot of things in parallel here, or the potential was to do things in parallel. We're updating this matrix here. It's a rank 1 update to the matrix, and there's a lot of things that could be done in parallel in that rank 1 update. So that was a positive thing, if you will, from that. The next decade brought about changing that algorithm. Instead of doing one column, what we did is went off on the side and computed a set of transformations that introduce zeros in this rectangle here, basically introduce zeros in this trapezoid. And that generated a set of transformations. And when you applied that set to the rest of the matrix, that application was a matrix product. It was a Schur's complement. It was a K rank update to the matrix. So we're going to update this green part of the matrix here by taking this matrix and this matrix, multiply them together, and updating that data. And because it was a matrix multiply, I got good performance, right? We can enhance the performance, get very close to the peak performance for the machine, and that was the goal. The goal was to effectively use the memory hierarchy of the machine to get good performance, and this accommodated that to a certain way, allowing for the factorization. So the factorizations were all structured along this way. It has some issues. It has some issues in the sense that it does this bulk synchronous processing, fork join. Every time I do one of these things, I have to fork off, and then I come back together to do something in a sequential thread. And that's going to hurt performance in the future as we look at things. And Scale-Pack did the same basic algorithm and just did it in a distributed way, passing messages around to effectively accommodate that situation. The schematic way of thinking of this algorithm is we're going to take this matrix and produce a factor of this column here, introduce zeros in this set of columns. That basically does an LU factorization of this rectangle of the matrix. And then we have to apply a set of transformations which update this part of the matrix, and then we do the matrix multiply. So that's sort of the sequence of steps. Those are the calls to the BLAS, if you will, that we're going to use to accommodate that sequence of steps. And if I look at this, how this is progressing, I basically have a sequential thread which goes through here, and then I do something in parallel, and then I can do another thing in parallel. So that's the loop-level parallelism that I have, that bulk synchronous processing, that fork join, which is okay if I have a few processors, but when I have 10 million processors, I can't do that. I can't do that fork join kind of processing. So the whole algorithm then gets structured like this. We introduce zeros in this rectangle. We move on to the next step, introduce zeros in this rectangle, and continue to do that until we complete the matrix. And that leads to a set of these fork join kind of things going on here. And if I look at the performance, let's say on a 16-core system, the performance looks something like this over time. So now I have a tool which monitors how the cores are behaving, what they're doing. If they're doing something productive, I light it up. So there's 16 columns here. I light up a core when it's doing something productive. If it's not doing anything, if it's idle, it's white. So in this model here, I see that my algorithm is exhibiting that chunk of time when it's doing something in parallel, but then there's also this chunk of time when one guy's doing something only. And then we continue with that process. So there's a lot of white space, and I don't want to see white space in my program, and I want to try to avoid that. So we think about how we can avoid that, how we can get more activity going on. And if we take a look at this problem here, what we're doing is we're computing something, and then we're applying it to this whole submatrix here. We're basically doing a matrix-matrix product, updating all the information here before we move on to the next step. So the question is, can I get ahead of myself somehow and start the second step before the first step is finished? Before I finish this matrix multiply here, can I really get started on the second step? And it doesn't take too long to see that if I just do a few columns, I can start the second step while I'm completing the matrix multiply on the remainder of that matrix. So what I do is basically structure the algorithm to do effectively that. I start the second step as soon as possible in order to accommodate as much things going on in parallel to overlap the operations. And of course, we don't stop at 2. We do as many of those things as we can. And that leads to an algorithm which is more like a data flow kind of algorithm. It leads to an algorithm which is changing the bulk synchronous nature of it. It's changing the way the algorithm is structured and is more like a data flow model in terms of its execution. So we go further and we divide up the matrix into tiles, as we call them, square blocks. And then we treat those blocks as independent operations when we can. And we basically evolve the computation identifying operations that can be done, in this case on the whole column, and then operations that can be done on these tiles so that we have a dependency graph of the overall computation, and that dependency graph is a directed acyclic graph of the computation. Now, we have to structure the data so that it respects those tiles. So we take our matrix, and instead of laying it out in its standard form, we lay it out in a tile form so that all the data within a tile is contiguous. So when I get a tile, I'm going to get access to the whole tile, and I can do that very quickly in terms of how data is moved. And that's important for performance in this context. So we're laying out our matrices not in this column-oriented fashion, but in this tile fashion. We prescribe a tile and then set the data into that form. And then the operations basically generate a directed acyclic graph of the program, and then we want to execute that DAG on the underlying structure. So our programs are written with, in some sense, the ability to generate this DAG, and then we need a model, a programming model that will allow us to execute that directed acyclic graph. So if you will, conceptually think of it like this. I go off on the side and generate the DAG, all the operations that are to be done, and then I have a runtime system which takes that DAG and executes it. If I had a perfect world, I might even compute the critical path, the longest path in this directed acyclic graph. And if I can execute that longest path, I'll free up the most parallelism. So that's the best case time. That would be ideal. I don't do that. I can't do that for various reasons. So what we're doing today is we're writing our programs using OpenMP as the programming model. OpenMP and version 4 has the ability to deal with tasks and has the ability to do dependencies within those tasks. So OpenMP is going to manage the tasking of this algorithm once it's been defined. And what that really means is in my program, if I have a call to, let's say, one of the BLAS operations, I have to define what's input and what's output. And that's how the tasks, then that's how the information about the tasks get communicated to OpenMP, and then OpenMP is the thing which is the task handler and monitors and executes that. And that's something which is quite simple in terms of the operations. If you take a look here at details, there's some pragmas that have been inserted into the code, which are the things for OpenMP. There's calls to various BLAS operations that can be seen under the covers here in terms of doing things like triangular multiplies, matrix multiplies here, rank K updates to matrices. So it's having a similar form that we had with the original LAPACK code, but now expressing it in a way which is exposing more of the dependencies, exposing more of the data flow associated with that, and allowing the underlying runtime system that's in OpenMP to effectively manage that. And that's basically what we get. We get a directed acyclic graph. That's a virtualized directed acyclic graph, which is being generated by the program, which is being handled by OpenMP because of the dependencies that are defined in the calls. And we get a result of this, this explicit parallelism. We get implicit communication that takes place. Things are done on a finer grain because of the block nature, these tiles that we have. And the result is that we get an execution. In the old days, looked like this for my program, which had bulk synchronous processing. The execution now gets compressed because I can expose more things to be done in parallel, and I get something which runs a lot faster. So that's the design that we have for the package we have called Plasma. So think of Plasma as the replacement for LAPACK. LAPACK was done in the last century. The new stuff is Plasma. Yeah. So statically scheduling says I could define ahead of time precisely where things go and how things can go. I can make that decision before the algorithm runs, except for things like LU, which require pivoting. That's correct, yeah. So if you don't have to make decisions about the data, you can do that. Or you can let it flow in the case of this. So this is dynamically scheduled. We just let it roll and let the operations go. You could always do a little better if you do it precisely, statically. We've done experiments where we did static and dynamic scheduling for these things, and it's marginal, the improvement. So the overhead of doing it, we felt, was not worth the benefit associated with it for these kind of algorithms. So we just let it flow. In fact, in the old days, OpenMP just came out with its tasking. In the old days, we wrote our own scheduler. So we had a scheduler called Quark, which did the scheduling for us. And basically, I would call Quark, tell it what operations were to be done, told it what the inputs and outputs were for those operations, and then it managed the back-end queue of tasks, and when the dependencies were satisfied, it started things, and so on and so forth. That was, I don't want to be in the business of writing a runtime. OpenMP has it. We're delighted its performance is as good as what we were doing. So that's sort of the story. These DAGs can be enormous. This is a small DAG, and I don't have the luxury of generating the DAG ahead of time. So the DAG is not is not generated and then executed. That would be an ideal world, because then I could find the critical path and execute the critical path. And I want these DAGs to be as wide as possible. The wider it is, the more parallelism is going to be in the application. So, so what we actually do, the reality is we generate a window of the DAG. So a window's generated. We may give hints as to where the important parts are in that DAG, and then we let the overall thing execute that, and we just scroll down the window till we complete the execution. So we're not working in an ideal world. There are some constraints. You can't store 1 million tasks and then analyze it and then do business. That's just too expensive to do. So in the real world, everything is dynamically handled. And we're doing this for all the algorithms. So we went through and redesigned, the whole thing. Let me stop and say this is not a new idea. The stuff we're doing here these are old ideas. Data flow has been around for a long time. These ideas have been around in books for as long as I can remember. My colleague Yves Robert has this stuff in detail in a book he did probably 25 years ago. So, these are not new things that we're creating. We're reusing new ideas, or the old ideas, in the setting of today's hardware. The hardware's here today, so it can be exploited, and these algorithms do a good job of exploiting today's hardware. And that's why they're in place today. They're very effective, and we can see improvements on it. So this is, we're looking at LAPAC run on this machine here. It's a 48-core shared memory thing. We're comparing it against LAPAC. We're comparing it against MKL. MKL is the Intel library where they spend a lot of time implementing things and trying to do a good job. There's a guy there called Goto who's superb at writing assembly language code for the Xeon processor. I think they lock him in a room and give him a new processor whenever it comes out, and emerges this incredible implementation of matrix multiply. So the LAPAC routines and compared to Plasma, it's just night and day situation on machines like this. Much better for performance. This is looking at LU. LU has some complicating features because of the pivoting that has to be done in LU. I know you can't read this in detail, but we went through a study of looking at different implementations of LU, looking at the case where we do no pivoting at all. You're going to get the wrong answer in that case. The algorithm is unstable, and without any correction to that, will lead to inaccuracies in it. And there are ways of accommodating for that, and we've tried to do some of the accommodations in these experiments that we did. And there's something called tournament pivoting, which Laura has some ownership of, and implementations were done with using tournament pivoting on this configuration and compared it in terms of the overall performance and doing things using the new way and the old way, and a merged way of doing business. And there's a paper describing this in gory detail. And in the end, depending on the implementation, you can get one that's much faster than the other in terms of its performance. QR factorization is another interesting case. QR factorization can be thought of so using orthogonal transformations to basically factor a matrix in preparation for doing, let's say, a least squares problem or something else. There's you can think about in the tiled case of introducing zeros by using this tile here to basically reduce others and do that in a parallel fashion. That's one way of forming the algorithm. The other way is to do this communication avoiding algorithm to minimize communication. Remember, communication's the thing which is going to kill your performance. To try to minimize communication by breaking it up into sections and then introducing zeros in parallel on sections of the matrix to effectively reduce it in perhaps a tree fashion, combining things and then ultimately computing the factorization. Again, there's many ideas here about the tree that's used and how the factorization should be performed, and you get many performance impacts as a result of that. So these are some experiments that were done. This is the LAPAC routine, doing it the old-fashioned way of fork-join parallelism. This is the MKL improvement on LAPAC, and then we have the ScalaPAC way. So we're running on a shared memory machine, and I'm going to run a message passing program on the shared memory machine to coordinate how the data is. Because I have control of messages, and I know explicitly what I'm passing around, I could probably do a better job than the system can with moving data around. So that performs better than these routines, because I have control over the data and how it's to be placed. The Plasma code, which does the directed acyclic graph version of this, has a performance which is an enhancement on that. And then if you do the communication avoiding algorithm for a tall and skinny matrix, this is a tall, skinny matrix associated with it. This is a matrix of roughly this size here, 51,000 by 3,000. you get even a performance enhancement over that. So depending on how things are structured, you have different choices of tools to use, but the point here is that we have to change the model, underlying model that we're thinking how the implementations are done. And the other thing that we have to be aware of, in the old days, when I grew up, you counted the number of floating point operations that your algorithm did, and then you counted up the number of operations for another algorithm, and that would tell you which one was better. You can't do that anymore. Right? That's out the window. Because of floating point, floating point has really been over-provided in these machines. It's free. Essentially, data movement's the expensive thing, so we have to worry about data movement almost more than we worry about the number of operations that you perform in your algorithm. So the more work you do may not translate into more time being spent, is the point. So here's an example of that. So this is the singular value decomposition. SVD is an important computation in many areas, and it basically is a two-stage process. We're going to take a matrix, this is for dense matrices, a matrix, and we're going to reduce it to a bidiagonal form. That's a direct process. You hit it with a set of orthogonal transformations on the left and right. You can reduce it to that bidiagonal form, and then you use an iterative process on the bidiagonal form to compute the singular values of the matrix, and then back transform to compute the singular vectors. So that's a standard way of doing it. That's the way we've been doing it for a long time. And that first part of the process is something, the first stage takes 8/3 n cubed operations, 8/3 n cubed to reduce the matrix to bidiagonal form. The iterative part, to compute the singular values, we know how to do that. We do it using the divide and conquer technique. It's well formed, and we're not going to change that. But this first part of the computation is a part of the computation which is taking a lot of time, and we think we can improve on it. So the LAPACK way of doing it works on panels of the matrix. So we're going to introduce zeros in this panel, and then we're going to apply it to the rest of the matrix. Remember I said these panels are done because we do matrix-matrix operations, and we learned that matrix multiply is a good thing to do. So we're on the right track here with matrix multiply. So this is looking at 3 generations of software. So I have the same platform. The platform is a parallel shared memory machine. It's a Sandy Bridge processor. It's a dual socket, 8 core. So there's 16 cores being used in this case. And we're going to run 3 versions of the software. IcePack. IcePack was the translation of Algol into Fortran. We're going to run it just turning on optimization. There's no BLAS in IcePack. So when you do that, we get some performance, and I'm going to normalize everything to that performance. So that has performance level 1. Then we're going to run the LAPACK code. The LAPACK code, we're going to run the LinPack code. LinPack has BLAS 1 operations, so it's going to be working on vector operations. I use MKL. I use the best version of those vector operations. And we see an improvement in the performance over IcePack. That's the blue line right here. You get a small improvement, maybe a few factor of 2 or 3 in terms of its improvement. And then I'm going to take LAPACK. I'm going to use LAPACK on 1 core, a single core of the thing, using level 3 BLAS operations whenever I can, turning up the optimization. And this is the performance I get when I use LAPACK. So again, a big performance over LinPack, and clearly a big hit, a big performance improvement over the original IcePack routine. So we're talking about an improvement of 5 times faster, right? That's what we're seeing here, 5 times faster for this guy here on 1 core. And then we let parallel processing take over. Parallel processing in LAPACK says we're going to do parallel processing in the BLAS operation. So I leave everything up to the BLAS, and we let the Intel people and Goto do its thing. And this is the performance we see in LAPACK over the IcePack routine. So we're 40 times faster than the original IcePack routine. IcePack did 1 core. This guy's using all of the 16 cores and doing it in a way which uses matrix matrix multiply to do it. It's using this algorithm here, which takes this matrix and reduces it, and then finds the finds the singular vectors of the matrix. The matrix is square in this case that we're dealing with. Okay, if we analyze what the LAPACK routine is doing, LAPACK takes the matrix, it looks at a panel, it introduces zeros in this panel here by a sequence of householder transformations, and then applies that on the left and right to effectively update this part of the matrix here, and then introduces zeros in this panel at the top. So that's the thing that when you run it to completion takes 8/3 n³ operations. If you look at what's going on in this procedure here of computing this panel stuff and applying it, we get two kinds of operations being done. We get a matrix vector operation and we get a matrix multiply operation. Half of the operations are coming from matrix vector and half are coming from the matrix multiply. So 4/3 n³ are matrix vector, 4/3 n³ are coming from matrix multiply. Remember on our previous graph, matrix vector operations were down in the dirt in terms of performance. Matrix multiply was at the sky. So this is going to limit the performance. In fact, it limits the performance. This algorithm is limited to 2 times the performance that we get from matrix vector. So we're killing performance because of this half of the work being done with matrix vector multiplies. So we're memory bound in this algorithm. And that's going to be the killer in terms of its performance. So we know we could do better if only we could do matrix multiply. Remember, it's because of this effect here. This is the matrix vector operation performance, and this is what we're hoping to get. But we're only going to be able to get 2 times the performance of this guy if we keep this algorithm in place. Okay, so the strategy that we're employing now is a 2-phase algorithm for reducing the matrix to bidiagonal form. The first phase of the algorithm reduces it to this, I'll call it a banded bidiagonal matrix. So we have a band associated with it, and that band width has something to do with the tile size. Let's call it 32 or 64 for the moment. So we're going to apply a sequence of transformations now, which take us from this matrix to this. That algorithm can be expressed fully in terms of matrix multiply. So I have something rich in matrix multiply operations. It's fully invested in this very rich operation. And not only that, it's very data flow oriented. I can organize that so I get overlap between stages and I can do many things in parallel. So I'm in a very good situation. Now I'm left with this matrix that I have to reduce to bidiagonal form to compute the singular values of. And I have an algorithm now which I call level 1.5 BLAS. So it's 1.5 BLAS because it uses a little bit of matrix vector, but it does use some vector operations. And that's an asynchronous, that can be made to be asynchronous, so I can do overlapping of things. And it can also be made cache friendly. So I have information in the cache, and I basically take this matrix here and take a piece of it and start chewing away at the upper bands of that matrix. Not on the whole thing, but just on a piece of it. And then later apply the transformations that are needed to the next piece and continue with that until I gnaw away at the matrix and get down to that bidiagonal form. And that's the algorithm that's currently in place in Plasma. And that algorithm takes more operations. So that algorithm does 10/3 n³ floating point operations. Those are coming from matrix multiply. And the second stage of the algorithm, it takes this much operations here. It's a term which is order n² in terms of the floating point operations. Remember, the original algorithm did 8/3 n³. This guy's doing about 25% more flops. So 25% more floating point operations, but the operations are richer in terms of matrix multiply. So that's the key thing here in terms of performance, is getting matrix multiply driven. So the results of that are that we get an algorithm which is improved over the LAPACK routine, over the one that we had that was doing very good in parallel, 6 times better than it in terms of the performance. And that comes about because of the matrix multiply. So we see an improvement that can be as much as 7 and 7 times enhancement in performance. It's doing more floating point operations, but it turns out to be 7 times faster. So the number of floating point operations is not a good indicator in terms of the time to solution. It really depends on the characteristic of those floating point operations. Let me pause and ask if there's any questions. And there are papers which talk about this in great detail, giving all the results, and there's software that's been implemented which exhibit this as well. The same thing can be done for eigenvalue problem. So eigenvalues have the same characteristic. There's a two-stage algorithm. So instead, for the symmetric eigenvalue, instead of going to tridiagonal form directly, we go to this banded form and then engage in a process which eats away at the upper band of the matrix. And again, we see this incredible enhancement over what we did with the traditional way of going directly to bidiagonal, going to tridiagonal. We get a big enhancement in terms of the overall structure. In this particular case, we're looking at computing all the vectors or some of the vectors or no vectors at all, getting the biggest advantage of this. The other thing, in a library setting, we're often faced with putting together library routines. So think about you want to solve a problem and you have to compose it using a number of routines. The classical way is you factor a matrix and then you call another routine to solve a system of equations based on the factorization. In this particular example, we're looking at computing the inverse of a symmetric positive definite matrix. You want to do variance covariance analysis or something, and you need the explicit inverse of a matrix. So the way you would do that is you would call a factorization routine for a symmetric positive definite matrix, so that factors the matrix. Then you call a routine which inverts one of those factors, and then you call a routine which multiplies that inverse to itself to compute the solution. And when you implement those three routines, you have a DAG for each of those routines, and if you look at the performance of that, this is the performance graph you would get. The first phase of the algorithm is used to factor the matrix. The second phase is used to compute the inverse of this this triangle, and then the third one is used to compute the multiply the triangle together by itself to compute the inverse, explicit inverse of the matrix. So we're showing matrices about this size. And that's fine. We were happy with that. You might be happy with that arrangement. But when we look at the DAG, we see that the DAG has components which perhaps can come together in the sense that we might be able to form a joint DAG, directed acyclic graph, which compresses this so that we don't have to wait for this guy to finish before we start up these operations. We can actually start them up much sooner, as soon as they're created in the overall structure of the tree. So we end up with a DAG which is much more compressed than we had before, and the runtime system is capable of dealing with that, and we end up with a much more compressed flow of information leading to a solution instead of taking this long, can be done in this long time. So that's another benefit that can be had from algorithms that are expressed in this way. Again, these are not new ideas. These are old things that have come about and are important to look at in this way. One of the things that we're looking at today is another set of operations for the BLAS. We see over and over again in applications the idea of working with small matrices, small BLAS operations, if you will, small matrix products. And we sometimes see them, many of them being posed at the same time. So if you think back on this directed acyclic graph, embodied in these nodes here, there's smaller matrix products, matrix multiplies, which are going on that can be done in parallel. And the idea here is to take those small matrix multiplies, matrices which have perhaps less than size 500 by 500, and have those parallel matrix multiplies to be done at one time. That is, put them together so they're not one after the other. We sort of batch them together in one call. So one call will get you a bunch of these independent matrix multiplies being done simultaneously. And inside the call, it's managed in a way that effectively uses the underlying hardware that we have at our disposal. So the goal is to be more efficient, to be parallel across systems, and we can show a considerable enhancement in terms of the overall execution. So again, coming back to this graph we've looked at before, this is looking at the new Intel Xeon Knights Landing. This is the matrix multiply performance for the Knights Landing. Knights Landing has up to 72 cores. The one we have in Tennessee only has 68 cores. So that's one chip with 68 cores. For matrix multiply for large matrices of size 20,000, it's running about 2.2 teraflops. So that's the execution rate. And again, matrix vector and vector operations, those are in the noise, so forget about it. So you really want to structure here. But the thing we notice, so that's the factor of 35. The thing we notice is at small sizes, the performance is not that good. Small sizes, the performance is substandard. I call this really where we want to be. Up to matrices of size 2,000, we're seeing performance which is not that good. So what we would like to do is, again, we have many, many matrices that we can pose to the architecture simultaneously. The problem is this guy has 68 cores. And 68 cores getting a matrix of size 50, there's not enough work there to use all 68 cores. So what we want to do is to give to that chip enough work to do, so maybe even independently, each of those cores could be working on one of those matrix products and doing it independently. So we're going to pose a number of problems independently and have it deal with that stream of work as fast as it can, rather than to have it do one at a time, where all the cores would be used and maybe not getting anywhere near the efficiency that we would hope for. So where does this come about? In machine learning. So deep learning, neural networks is a big deal today, right? I think it's going to become more of an important thing in scientific computing, using deep learning to understand trends and to figure out what the way things are going. And in these neural network problems, they effectively deal with matrix multiply. So matrix multiply is the computational kernel that they have. And the matrices are relatively small. So the matrices they're dealing with are matrices that can be of size 50 by 50. And they can have thousands of them. And they're all independent right at the same moment. So today, the hardware, if you posed each of those in a sequential way to the hardware, you get very poor performance. So what we're proposing is having one call where you pose all of those simultaneously and then manage within the structure of that call how you deal with those operations. And with neural networks, you can actually get by with less than 64-bit arithmetic. Today, they're building hardware for these guys that do 16-bit floating point arithmetic. So forget about 32. Single precision, you can get by with 16. And I've heard people say, I don't even need 16. I can get by with integer operations for their problems. So there's an area there that we can perhaps help with. And another place where this comes up is in my dense matrix calculations. I work with these tiles, and those tiles are independent. So when I do the Schur complement, I have these matrices times these matrices updating all of these, and those are independent operations. So I can pose them as independent operations to that call that would be made. And for sparse direct methods, where I'm dealing with a matrix using a multi-frontal scheme, I have independent, it doesn't come out very well, I have independent fronts that I deal with, which have dense matrices, and those dense matrices can be posed and handed off to the underlying routine and done in a much more efficient way. So what we're proposing is, instead of dealing with a situation like this on today's systems, where we make one call in a loop, looping over each of those matrices one after the other, we pose them as a batch. We make a call which has all the data being entered into into the call itself with a count associated with it. The matrices may or may not have the same size, and the underlying routines would effectively accommodate for that, and getting much better effective use of the underlying hardware. And when you do that, you do see an improvement in performance. This is looking at, again, that Knight's Landing thing. Here we have different sizes. We have 4,000 matrices in a call. We're posing 4,000 matrices. In this case, matrices have size 32, 64, and so on, up to 512. And we see this enhancement in performance that we see for these kinds of operations. So we get a factor of 3 performance improvement when making calls in this way. And the same is true even on more conventional processors. This is done on a 16-core, more conventional processor from Intel. So that's these are new things which are just being thought about. We have a standard for this, and that standard is going to be pushed forward. And we have an implementation, of course, and that standard will be pushed forward. And look for community comment, and ultimately it would be implemented and used for these kind of things. I want to talk a little bit about mixed precision. We think of doing the computation in 64-bit arithmetic, and we know that 32-bit arithmetic is twice as fast. So the question now is, can we do something with that 32-bit arithmetic and get the performance of enhancement while still getting the same accuracy out? That would be the goal. So what can we do in that case? So improve runtime, reduce power consumption, lower data movement. That's all important, and you could do that if you do work with 32-bit arithmetic. You know, in some cases, if we think about computing the next iteration, maybe framing the problem not in terms of computing the next iteration, but in terms of computing the correction to the problem, the correction to the next iteration. And so you're going to be making a correction. You have some accuracy, and you're going to be making some correction to the accuracy. So you're going to be adding bits out in the end of that sequence, similar to Newton's method and the way it works. So exploit 32-bit precision in the core of the operation, where you're doing most of the work, and then switch to 64-bit computation to refine the accuracy. Okay, so that's sort of the intuitive thing, is to compute the 32-bit result and then compute a correction to the 32-bit result in higher precision, and do that until you get to the desired accuracy. So here's an algorithm that we have in our toolbox. It's called iterative refinement. So iterative refinement says we're going to compute a factorization for the matrix. We're going to compute a solution using that factorization. And then we're going to try to enhance the accuracy of that solution. And we do that by computing a residual. And the residual has to be computed with the original data, though. So that's one of the important aspects of this operation. You must use the original data, the original matrix, to compute that. Usually the factorization consumes the original matrix. You overwrite it, but you have to keep a copy of it. And then you're going to go through an iterative process using that residual as the right-hand side, and that solution that you get actually turns out to be a correction to the solution. So that's a well-known property. It's a little bit too much to deal with here, but that's what happens in this situation, that the residual, when used as the right-hand side, gives you a correction to the solution, and then you think about computing a new residual, and then you iterate on that. And you iterate until you converge to a desired thing. So this is a well-known thing. A lot of people have looked at this and studied it and provided error bounds for it. And you could show that if you selectively use single precision and double precision, you're going to converge to a solution which is as good as the double precision solution. So taking a look at this work here, the first step is doing the factorization. That takes n cubed operations. Solving the system calls is n squared. Computing a residual is n squared. Computing another solution is n squared, and so on and so forth. So the real expensive thing is the factorization. So we're going to compute the factorization in single precision. So the idea here is to selectively use single and double precision. So I'm going to selectively use single precision for the factorization. I compute the solution in single precision, so now I've got a single precision result. I compute a residual in double precision, so I need the original data. I compute this, elevating those guys to double precision, the solution to double precision, compute the residual in double precision, and then iterate, compute this correction in single precision, add the results in double precision, and then compute a residual in double precision. And you can show when this converges, you're going to converge to the solution that you would have gotten had you solved the original problem in double precision. And the advantage is I've done this thing here in single precision. So I'm doing the bulk of the work in single precision. So I would expect this to run faster. I would expect it to asymptotically run at the speed of single precision if it converges. So n cubed work is being done in lower precision, n squared work in higher precision, and there's some issues. First off, I have to have a copy of the matrix. So I have 1.5 copies of the matrix. 1 copy in double precision, 1 copy in single precision. Single precision got factored. Double precision copy of the matrix is the original data, which I use to compute the residual. So 1.5 copies of the data. I have to converge. The matrix will converge as long as it's not too ill-conditioned. I have to get 1 digit right in that solution. The first solution there, I have to get 1 digit. If I get 1 digit correct, then I'll converge. The convergence may be a little slow, one digit per iteration, but if it's well conditioned, it goes in 2 iterations. I get the right solution in double precision. So the matrix has to be moderately well conditioned. I can't be higher than 10 to the 8th. I have to get 1 digit correct. And if I get 1 digit correct, then I'm in good business. So we've implemented this. This is a routine now in part of LAPAC, and it'll be part of Plasma as well. So here's what happens. Forget about that algorithm for the moment. This is what happens when you run on some hardware, on this hardware, this happens to be a GPU. In single precision, this is what I get if I solve a problem for different size problems, and this is what I get if I solve that problem in double precision. So there's that factor of 2, right? I'm getting a factor of 2 because of the speed of single precision is twice as fast, and I'm moving less data around. Moving less data around is a critical thing. So I get that factor of 2. Now, iterative refinement. Iterative refinement is going to factor the matrix at this speed and then do selectively double precision in an iterative procedure. And it turns out that we can enhance the performance. So this is the result, the performance result we get when we compute the result in using iterative refinement, doing single precision factorization, and then selectively double precision, enhancing the results. So we get something which is more closely related to the performance of single precision than it is the double precision result, and turns out to be much faster in terms of the time. So in all of these cases here, I've used the same number of floating point operations to compute the rate, so it's on a fair and equal basis for the rate of execution. So that's a trick that can be used for dense matrices, but it also has been applied to sparse iterative methods. So where we think about an inner and outer iteration, where we do the inner iteration using additional precision and the outer iteration using less precision, you can come up with a scheme to accommodate that and drive that to convergence, getting higher precision, getting a lower, getting a higher rate of execution, lower time to solution. Okay. So, some of the conventional wisdom we have of doing work on these machines may not be holding today. The conventional wisdom said that the peak clock frequency is the primary limiting factor for performance. And, today power is a limiting factor in terms of the design of these computers. We really have to be concerned about how much power this processor and how much power the overall system is using in terms of what we can put in place, not the clock, not necessarily the clock frequency. The cost, the floating point operations is the biggest cost for doing things. That's the old conventional wisdom. And today, we know data movement dominates the cost associated with this, and minimizing data is something which is going to enhance the overall effectiveness of our underlying algorithm. Modest growth in parallelism by adding nodes was the old conventional wisdom. And today we got this explosive growth in terms of parallelism within the chip. We have chips which have 260 cores. That's going to grow. The Chinese are talking about enhancing that product to potentially have 1,000 cores in that one chip in their next design. So of course they're designing the follow-on thing to go to Exascale, and that's roughly what we need for Exascale-based computing. And we know of our own designs in the US. Intel has something called Knight's Landing. The next generation, Knight's Hill, is going to do something to enhance the number of cores, to put more memory on the socket itself, and to expand things in a way which gives us this incredible growth in terms of parallelism. Memory scaling, we want to maintain the bytes per flop capacity and bandwidth. That would be a nice thing if we can do it. The memory scaling today is growing at this incredible rate, outstripping really the rate at which we can move data around within the machine. We get this uniform, we think of a uniform system performance associated with a given set of processors, and today we get this non-uniform behavior that's occurring. The non-uniform behavior comes about, in a number of ways. We talked about my laptop having this thing called Turbo Boost. Turbo Boost kicks in, and I don't know that it's kicked in. It kicks in because of the conditions on the chip. The chip conditions are such that it's not going to get too hot, and it can enhance the frequency of that chip. That's beyond my control, and that gives this chip the ability to do more floating point. So I thought I had a unified, if I think about a set of processors, I thought I had a unified set of processors that would all start and finish a computation with the same work at the same time, and it's not going to be the case. So things are going to be changing in terms of the time to solution based on things I can't predict. I have no control over. So it causes all sorts of jitter when we take a look at the performance of our algorithms, all sorts of unusual behavior. In fact, we have this measurement of theoretical peak performance for processors. And with the LINPACK benchmark, we show the theoretical peak performance, and then we show the achieved performance. And some of the machines on the list get a number like above 90% of peak performance. And getting 90% for that benchmark is very hard to do. And I thought originally they were cheating, because I didn't think that was possible. And then what happens is, we compute the theoretical rate of execution of a processor based on the cycle time that's listed. But that doesn't include the turbo boost, which bumps the thing up in a way that I can't predict. So what's happening on many of those things is turbo boost is kicking in, raising the cycle time so that it has a higher potential than what we rate it at, and as a result, they're getting more than they deserve, let's say, in terms of the percent of peak performance. And reliability. So, in the old days, we had this assumption that reliability should be part of the hardware problem. And today, we really have to be involved in the reliability of our computation. So we're designing software today that can recover. So the model today is, if you lose a process, an MPI process, your application will fall over. So you had better do a checkpoint so that you can restart. If you're running something for 20 hours, it's essential that you be able to recover from that in some graceful way. So checkpointing is the model that's used today. And we're working towards having MPI have a mechanism within MPI so that it can correct, it can do something based on failure. So if you lose a process, the application doesn't fall over, it can maybe give control back to the user, and then the user could do something to recover from that fault. And today we're designing software that can do effectively that. That is, if you lose an MPI process, the computation can basically recreate something and then carry on the computation based on what's ever going on. And we're going further in trying to not only recover from what I'll call hard failure, so a hard failure is losing a process, but also recover from soft failure. Soft failure is when you have a bit flip. So you lost something, you have to be able to detect that you've lost something, and then you want to be able to recover from it in some graceful way. So there are techniques, there's techniques that are old ideas, algorithm-based fault tolerance, where you carry checkpoint along with the computation so that checkpoint can then be used to detect when a problem has occurred, and that checkpoint can actually be used to recover the failure, the bit flip, and continue on with the computation in the presence of that bit flip. So those are ideas that are happening in today's world, and we're in the process of looking at that as a software base for future machines, and especially for machines that we have that are going under Exascale. Okay, so the question is, can we build an Exascale machine today? So we have a machine which runs at 125, or has a peak performance of 125 petaflops, right? That's the new Chinese machine. So can we build an Exascale machine? So it's an order of magnitude greater, right? And sure, we put 10 of those guys together, we can build an Exascale machine. So that would require 150 megawatts of power. Remember, it's $1 million a year per megawatt, so that's $150 million to turn the machine on. It would have 100 million threads of execution, and it would probably cost about $2.7 billion. So that seems unrealistic. So the technology isn't ready today to build an Exascale machine, right? But maybe it will be soon. So the question is, what will it look like? So this is the #1 machine today. So this machine has a peak performance of 125 petaflops. It has 15 megawatts is the power consumption. So that's 8 gigaflops per watt. That's its efficiency, if you will, 8 gigaflops per watt. That's theoretical peak number. It has 1.3 petabytes of memory. It has certain performance. Each node in that machine is 3 teraflops. It has 260 core. It's 16 gigabytes per second is the rate at which we move data inside the machine. It has 40,000 nodes. It has concurrency about 10 million. That's the number of cores. 1 thread per core for this machine. And the failures, they probably have a few failures per day. I don't know the exact number, but I would guess things are breaking on that machine. Something's going wrong with the processors. Something's going wrong with the network. There's some software glitches that are causing a few failures. So if you were running the machine at scale, one application running on the whole machine, you would see the machine fall over a few times a day. And if you didn't do a checkpoint, then you'd have to restart from the beginning. If you did a checkpoint, then you read your checkpoint in and restart your application from that last point. In the US, the general goal here is to build an Exascale machine for $200 million. So that's sort of the standard price for #1 machine. High performance machines are about that. And the challenge is to build it at 20 megawatts. So the Department of Energy has said those are the 2 parameters that you can work with. It's a challenge. Can you do it for $200 million, and can you do it for 20 megawatts? If it's higher, I think it'll be okay. If it's a lot higher, probably then there's a problem associated with it. So, the Chinese are saying they're going to build it in 2020. In the US, we're saying 2023. And here's what that machine would look like. It would be an exaflop. It would be around 20 megawatts, so that's 50 gigaflops per watt. So that's about a 6 times enhancement we need. We need 6 times better efficiency than what we got today. So that's a big deal. The memory, so the way this works with memory is you're going to spend half the money on memory. So memory is pretty expensive. You're going to spend half of it, and you can probably buy, in this time frame, somewhere between 32 and 64 petabytes of memory. Probably 32 is the number that's going to be purchasable. So you got about 32 petabytes of memory, maybe 64. And in terms of the flop rate per node, we're thinking about something on this order, 1.2 up to 15 teraflops per node. Right now we're at 3 teraflops. In terms of the concurrency, somewhere between 1,000 threads of execution up to 10,000 threads per node. A single node having that. Remember, we're at 260 today in terms of the number one machine. In terms of the internode bandwidth, moving data between the nodes, we got we got 16 today. We're looking at something around an order of magnitude 20 times faster is going to be needed to get to that point. 40,000 nodes, and here we're thinking about 100,000 nodes, up to maybe 1 million nodes in this machine. So somewhere between 6 and 60 enhancement. The concurrency is at 10 million, and the Exascale machine, we're thinking about 1 billion threads of execution is what's going to be needed to maintain that. So you would have to orchestrate something on the order of 1 billion threads of execution, and they're assuming they're going to have many failures per day associated with that. So there's really a tremendous number of challenges associated with that in terms of the power consumption for the machine getting up to 50 gigaflops per watt, in terms of the concurrency, being able to manage that level of concurrency 100 times more than we have today with that number one machine. And the mean time between failure is going to be a big issue with this hardware in place. We have big machines today. There was an interesting article that was written in the IEEE Spectrum a couple months ago, and it talked about the Oak Ridge machine. It talked about the problems they had in getting the machine up. And the thing that struck me was, memory's protected. So there's ECC to protect memory. So memory has extra bits associated with it, so that if something happens to one of the bits, you can detect and correct one bit flip in a byte, 1 bit flip. And if you have two things going on with those 8 bytes, you can detect it, but you can't correct it. So that would be a thing which would basically stop the machine in that situation. So the machine we have at Oak Ridge has a lot of memory. It has, I think it has less than one. It's probably maybe about half of that. It has about 0.7 petabytes of memory sitting inside the Oak Ridge machine. And the thing that struck me in the article, it said that ECC, they were seeing something on the order of 130 ECC errors per minute. 130 errors per minute. I found that stunning. So the hardware's correcting that number of bit flips across the memory per minute. 130, that's incredible to me, right? The hardware's in place to do that, so it's doing its job. And they have they have a parity of, they have 2 faults occurring. I think it's a couple times a week. They have two bits that are being affected, that 2 bits get flipped. And they have to stop them, then your application falls over. You have nothing there to correct it. But 130 per minute, that's a stunning number. I found that to be just incredible. And the hardware's protecting us from that. So that's, as we get more memory in our machines, that's going to be a bigger and bigger thing, I feel, being able to protect all of that memory in that way.
So that's a real number? You see every day a few nodes fall? That's based on new machines standing up. A few nodes fall over per day. That's a common thing. So the machine at Oak Ridge, a few nodes fall over.
The guys at Livermore with their Sequoia machine, they reported the same thing, a few per day, when the machine first stood up. After the machine is burned in, we don't have that failure rate anymore. In fact, the machine at Oak Ridge was terrible. The machine at Oak Ridge is it's AMD plus NVIDIA. So Cray made boards which put NVIDIA cards and then the AMD chips, and there's solder connections between them. And after the machine was working, they noticed they were getting the wrong results. Nothing was coming back reporting wrong results, but the guy says, my results are wrong. So they were checking into it, and they determined that there was a problem with the connection between, on the PCI Express bus, connecting the GPU, the NVIDIA card, with the AMD processor. The solder joints had bubbles in them. Solder joints had bubbles, and those bubbles under heat stress were causing things to flex enough so that they would lose connection between it, and that wasn't being detected. Turns out that they claimed they used too much gold in the solder to cause the bubbling to occur, and so they had to replace all the boards had to be replaced over months period of time, which was an incredible thing. Yeah.
Yeah, I guess you know about this Mont project.
Yes.
Where they use very cheap hardware and they don't have ECC on the memory. There is this, so this is just an experiment.
Yes. Wow.
But there is this paper where they show that they have a lot of bit flips, obviously, but there is a strong locality, and only a few nodes are at the origin of most of the bit flips. So basically, you just have to remove those from your
I see.
execution, and then you don't get that many bit flips.
Right.
Isn't that a hardware problem still that we could solve by saying, let's actually see if the hardware is good?
Yeah.
We have a lot of heterogeneity in
Yeah.
the supercomputer.
Yeah. So ECC costs something. It costs extra bits are used, and then there's time spent to make sure to see if you got the right answer, and then to correct it if it's wrong. So it is an expense. So you might be tempted to turn it off, and the people at Barcelona are tempted to turn it off. To experiment. Experiments are good things, absolutely. So I think that's interesting. That's an interesting data point. I have people coming to me and saying, I've got this big machine which has these GPUs in it, and with the GPU you can turn off ECC. So the GPU memory is not protected then. And I say, I don't know if I want to do that. That's a dangerous thing to do, because you won't be told when you got a problem, and you probably will have some problems.
Yeah, my question was more, we all know the way Intel sells their CPUs.
Yeah.
They build a lot of them, then they test them.
Yeah, absolutely.
If they work, they sell it to you. If they don't work that well, they sell it at a cheaper price.
Yes.
Lower frequency, and if it doesn't work at all, they don't buy it.
Of course.
But couldn't we just improve the quality we require and reduce this TTF a lot?
So if we trusted the companies to do what you say, perhaps. But what's happening is we buy chips, we buy processors from this company, and memory is bought from some other company, and we hope that memory is good quality memory, and sometimes it is, and sometimes it isn't. And just as you point out, sometimes you get batches of it which are not quite up to the right standard, and incur bit flips and other things to cause damage. So I would be cautious of that. I would be very cautious. So there's also a story. The top 500 thing has many stories associated with it, but one story is there was a group at Virginia Tech who wanted to have a machine on the top 500, and they went to Apple, and they purchased a bunch of Apple workstations and put them together, desk-side machines, and put them together in a rack, and fired that up and were running. And they noticed they were getting a lot of failures. And the failures were caused because those machines were not ECC memory checked. So they were getting errors on that. And in the end, they had to replace all those with rack-mounted boards that were effectively the same thing, which were ECC checked. And so I would say you got to be a little bit careful about that. My hardware friends say that this problem of hardware errors is not going to be there. They're going to make the hardware so robust that it will not fail. I'm not taking them to, I want to protect, I want to have a plan B. So we have algorithms which will, when implemented, can detect failure and then recover from that in some graceful way.
Historically, right, we've had this discussion before. We had it for the terascale machines and the petascale machines, and now it's the exascale machines. And each one is supposed to be completely unreliable. But people that sell unreliable machines go out of business. And so it has happened that each time we've had this and the predictions are made based on these kind of Poisson estimates,
Yeah.
they don't happen.
Right, the machines work. They are working, and they are working remarkably well. We do get failures, though, that occur, and they have to be protected in some way. If I'm designing a plane, I want to make sure I didn't do the wrong design, but we have other ways of checking that too. So that's something that has to be built into everything, hopefully. You don't want to get into a situation of blindly relying on whatever comes out of the computer. You have to have other checks that are there as well. Absolutely. Okay, let me carry on with the stories. So this is what's happening in the US. So the US has a plan to deploy 3 big machines, and that's going to be starting at the end of 2017, and everything's going to be operational in 2018. So they're going to spend $500 million, and they're going to buy 3 machines. They're going to put one at Oak Ridge, my place. They're going to put one at Lawrence Livermore Lab, and those are going to be IBM-based. IBM with NVIDIA cards, that's the plan. Next generation IBM processor, next generation NVIDIA with much faster interconnect, NVLink, all sorts of magic stuff. And Argonne's going to get a machine that's Intel-based. So Intel-based machine is Knight's Hill. That's the machine beyond the current thing we have. Many more cores, a lot more memory. It's almost going to look like, if you remember that we've talked about in the past, computer guys have talked about processor in memory. So it's going to sort of have much a characterization of that. Again, it's because data movement's so expensive. You want to move processing to the memory locations. And so these 3 machines will come in 2018. And the machine after that is going to be Exascale in the US. That's the goal. The Exascale machine is now thought to be 2023, but that could be accelerated. The acceleration can come about because of the Chinese. So I don't have that slide here, but something that happened in the US in February was the Chinese were planning to upgrade their Tianhe 2 machine, which is an Intel-based machine. So it's all Intel. It has Intel Xeon 5 plus Intel commodity parts. They were planning to upgrade the Intel Xeon 5 with the new ones, the Knight's Landing. So they placed an order for replacing all of that with the new Intel chips. And they had already improved their interconnect network. So they made their own interconnect faster. And then the US Department of Commerce said, no, you can't do that. It embargoed Intel from selling chips to 4 places in China. The 4 places were the 4 places that build the high-performance machines or use them. So the National University for Defense Technology was the guys who did the integration. They're prohibited from buying Intel parts. The National Supercomputing Center in Guangzhou, where the supercomputer is located, they're prohibited. The Supercomputing Center in Tianjin, which is the old version of that machine, is prohibited. And I think the guys in Wuxi also were prohibited. So the US decided to prevent Intel from selling them parts. And the result of that is China went off and built their own stuff. So I think that was a fitting end. The upgrade that was to occur with Intel, the new Knight's Landing processor, they're going to upgrade the machine, the Tianhe 2, it'll be Tianhe 2A, and that machine will be based on ARM processor plus an accelerator that they developed themselves. So ARM is about to announce a new processor next month, in fact, ARM V8A something or other. So that'll be a 64-bit floating point engine which can do high performance. So there are no ARM processors on the top 500 list. No, I think that's going to change. They're going to have many ARM processors soon. You probably are aware that Japan recently bought ARM, so that's another indicator that things will change in some way. So I find those situations interesting in many ways. Okay, so here's exascale machine. There's sort of two ways of thinking about it. We have to get to 10 to the 18. So how do you get to the 10 to the 18? Well, we have a gigahertz processor. We have 1,000 cores per socket. And then we have 1 million of those sockets. So 9, 3, and 6, that gets us to 18. So that's a potential machine, right? So 1 million sockets seems like a lot, to be honest, but that's a potential machine. These two numbers don't. A hybrid way of thinking is to have a gigahertz processor, to have 10,000 of these things, FPUs on a socket. These are floating point units, so think of them as threads of execution in some sense, and then have 100,000 of those sockets in a machine. And again, 9, 4, and 5 gets to 10 to the 18. So I would say those are two potential paths to the future machine. The Chinese look like they're building in this regime here, so that may be one way of going. Let's see, where do we want to go next is the question. So we have 10 minutes left. Okay, let's, the classical way of, this is some conclusions here. The classical analysis of algorithms, you got to be a little bit careful how we do it. Floating point operations is not the only thing to look at. It's what kind of computations are done, and data movement is critical in all of these things here. Algorithms and software have to take advantage of that data, reduce data motion. Bandwidth and latency are big issues. We need latency-tolerant algorithms. Communication and synchronization reducing algorithms are going to be a big deal. The hardware that we have really is presenting us with a dynamic situation that has to be accommodated for somehow in the underlying environment that we're running on. That has to be also dealt with in this way. Existing algorithms that we have today really can't exploit all the features that we have. Okay, so I've said some of this. So here are the things that I sort of think are exciting from the standpoint of moving forward and designing things and looking at how we structure things for future algorithms and software. So synchronization reducing algorithms are key for some of these things. We've got to break that fork join model. The directed acyclic graphs do a pretty good job of that. Not all algorithms can fall into that form, but that's certainly an important thing to do. Reduce communication. Have algorithms which can achieve the lower bound possible for a given algorithm. My colleague Jim Demmel has sort of cornered the market in terms of looking at algorithms and defining what the minimum communication is for a given algorithm, and then we come up with algorithms that fall within that bound somehow, and that's going to be a key and critical thing to do. Mixed precision can lead to some advantages, getting the speed advantage of half precision, then with data motion also being enhanced because you're moving around 32-bit rather than 64-bit operands. Auto-tuning is going to be critical here when we have such a complex machine that we're faced with. Auto-tuning in the sense that, I can't leave it up to the user to adjust all the knobs and dials on a given piece of software. That software has to be driven in some sense by the software itself. That is, the algorithm there has to be adjusted dynamically to take advantage of that dynamic situation that's occurring within our computers today. We thought about auto-tuning in the old days as being static. You went off on the side and did something that set parameters that you use from that point on. But now I think auto-tuning has to be embedded into the software and run with the software to change things based on the conditions that we have. Fault resilience, building into the algorithm the ability to detect and correct failures, I think is an interesting area that should be explored. There's a lot of research that has been done and can be applied to some of the models that we have today. And you know, reproducibility is a thing that we often take for granted in some sense, and it's sort of a missed. It's sort of missed, I think. So you know, I can't guarantee today that if I do a computation on a computer, I'm going to get the same results if I redo that same computation on that same computer. I may not get the same result. Now, we're numerical guys, so we get it. You know, I have error bounds that I can tell you about the computation. As long as it satisfies the error bounds, we should be happy. You know, my friends in physics and biology, they put their error bars around their graphs, and they're happy with that. But some people insist on getting the same answer, so that if they run today and tomorrow on the same hardware with the same software, they demand the same answers come out of that computer. I find that to be a bit strange and extreme, but you know, they're yelling enough that we have to provide that in the software layers. So you know, that in a simple case, it amounts to making sure that the collective operations get done in the same order. So today I can't guarantee that. When I sum up numbers, I can't guarantee the order that they're going to be summed up. And that leads to round-off error, which may be different today and tomorrow because the order is different, and I may get slightly different results. And of course, that could be magnified by the ill conditioning in the problem, but you know, we get that. We understand what the error bounds are, but some people are alarmed and shocked at that. So we get this from the MathWorks. So the MathWorks guys use our software. So when you type A/B, you're using my software, and they insist that you get the same answer today and tomorrow when you type A/B. And I tell them, look, I can't guarantee that. If I can, if you want me to, but it's going to be more expensive. So that's the price that'll be paid in that context. And then some, you know, the guys who are doing nuclear reactors, they have to guarantee that for some reason. And to be honest, if I'm debugging a program, I want to get the same answer today and tomorrow. Otherwise, I may not know where the problem lies. So there's some good reasons for doing that. So we're coming up with ideas and ways of satisfying reproducibility. Jim Demmel is leading an effort to try to get that implemented in a way that makes sense. He's doing something with the IEEE standards today. I think that's looking into this issue in more detail. So maybe they'll have something there. So that's really what I wanted to talk about. There's a paper that was done back in February which talked about 10 challenges for Exascale. The stuff in there is still relevant today. It talks about the 10 critical things, and they're interesting to look at. They deal with energy efficiency, interconnect technology, and memory technology. Those are hardware issues. It talks about some software issues, scalable software, programming systems, data management, and scientific productivity that's related to software. And then there are algorithmic issues about trying to come up with reformulating problems so that they can effectively be used on exascale systems, doing refactoring, algorithm discovery and design, and then resilience and correction. So those are sort of things that the Department of Energy at least discussed or focused on for that. So let me conclude there, and I'd be happy to answer any questions in the remaining 5 minutes.
Okay, so let's find questions?
Guys are all hungry. Yes, Martin.
We have seen that iterative methods have really very bad performance on these systems, and the way I think you explained it is that you cannot get block operations for those. You just produce vectors by vectors. Is there no way to write iterative methods also in a blocked form?
Well, remember, not only does it have to be blocked, but it's got to be matrix form. So you, yeah. And
No way to write an iterative method like this?
I don't know of a way. Maybe we should look at that and try to structure things in a way that can express the algorithm so that you're effectively doing a matrix multiply.
You can use block relove.
There's block methods, but that's matrix times vector.
But there are
So-
fundamental limits on that Like if you look at what Traub does and when he says, let's look at what you can say is like an efficiency index of an iterative method, right? So it's how much information goes in and how much, what kind of convergence rate do I have? And Newton, for just having that bit of information, the Jacobian information, it's optimal. And there are multi-point iterations, and he has a whole book, Iterative Methods, where he goes over all these multi-points, and you can formulate those as that, but all of them are asymptotically less efficient. So we don't know of some optimally efficient method where we're using more pieces of data.
Okay. So the answer is unknown?
Yes.
Okay.
It's an area of active research.
Other questions? So if there are no more questions, let's thank Jack again.
So that's a picture of the 4 people who did LinPack. That's Cleve Moeller. So Cleve gave us MATLAB and a bunch of other things. That's Pete Stewart. So Pete does numerical linear algebra. He just retired from Maryland. That's Jim Bunch. He's at San Diego, or was at San Diego, University of California, San Diego. He retired from there recently. That's me, a previous version with a little bit more hair. This is my car. This is my license plate. That's from 1979, I think. And yeah, lots changed since then, as they say.